In the vast and mysterious depths of the universe, where black holes typically grow to mind-boggling sizes, one stands out as an intriguing anomaly: XTE J1650-500. Thought to be the smallest known black hole, this cosmic object challenges everything we know about stellar evolution and the boundaries of black hole formation. Discovered in the early 2000s, XTE J1650-500 offers a unique glimpse into the enigmatic world of compact objects, with its surprisingly low mass raising questions about the very limits of black hole creation. What makes it so captivating isn't just its size, but the mystery surrounding its formation, behavior, and the incredible forces at play within it. Let us begin at the edge of this cosmic enigma. Discovered in the year 2001 by NASA's Rossy X-ray Timing Explorer, XTE J1650-500 is what astronomers call an X-ray binary system. These are celestial systems that emit copious amounts of X-rays, produced by the intense gravitational tug of a compact object, either a neutron star or a black hole, on a companion star. In the case of XTE J1650-500, observations pointed to a black hole candidate as the source of these emissions. But this wasn't just any black hole. The data began to hint at something astonishing. Its mass appeared to be only about 3.8 solar masses, possibly less. That figure danced precariously close to the theoretical lower limit for black hole formation, which is somewhere near 3 solar masses. Below that, gravitational collapse typically results in a neutron star, not a black hole. This placed XTE J1650-500 in a twilight zone, a strange cosmic gray area, where the distinction between the most massive neutron star and the lightest black hole blurred into an astronomical mystery. But why does this matter? To understand the significance, we must dive into the basics of stellar evolution. When massive stars exhaust their nuclear fuel, they undergo a catastrophic collapse. The outcome of this collapse depends on the mass of the remaining stellar core. If the core is under 1.4 times the mass of our Sun, the so-called Chandrasekhar limit, it becomes a white dwarf. If it's between roughly 1.4 and 3 solar masses, it collapses into a neutron star, an ultra-dense object composed almost entirely of neutrons. But above that threshold, usually pegged around 3 solar masses, the collapse becomes unstoppable. Not even neutron degeneracy pressure, the quantum force resisting further compression, can halt it. The result is a black hole. But these are theoretical boundaries, built on physics we understand imperfectly. In reality, the lines are blurrier. And this is where XTE J1650-500 enters the scene like a whisper from the unknown. If it truly is a black hole of less than 4 solar masses, it challenges our models. It nudges us to revisit our equations. It reminds us that even in the cosmos, the smallest voices can carry the loudest questions. Let's go back to its discovery. The Rossy X-ray Timing Explorer was one of NASA's key instruments for detecting cosmic X-ray sources. Launched in 1995, RXT was designed to observe the variability of X-ray sources, including neutron stars, black holes, and active galactic nuclei. When RXT detected an outburst of X-rays from the coordinates that would later be attributed to XTE J1650-500, astronomers took notice. This was not just a random flare. The X-ray light curve, how the brightness changed over time, revealed periodic signals that hinted at the presence of a compact object. Over time, and with follow-up observations using both space and ground-based telescopes, astronomers identified a binary system located approximately 10,000 light-years away in the constellation Era, deep in the southern sky. The system appeared to consist of a low-mass companion star orbiting an invisible but incredibly dense object. The orbital period was just a few hours, a cosmic dance of close companionship. And the only explanation for the X-ray emissions, as well as the gravitational dynamics, was the presence of a compact object pulling matter from its partner. As this matter spiraled inward, it formed an accretion disk, heating up to millions of degrees and emitting powerful X-rays. This is a classic hallmark of a black hole binary. However, things got more fascinating when researchers tried to calculate the mass of the invisible object. Based on the motion of the companion star, how it moved due to the gravitational tug of its partner, they were able to estimate a mass function, a mathematical relationship that helps determine the minimum possible mass of the compact object. That minimum value was about 3.8 solar masses. Given observational uncertainties, some estimates even dipped as low as 2.7 solar masses, dangerously close to the maximum mass theorized for a neutron star. This presented a paradox. Was this truly a black hole? Or could it possibly be an incredibly massive neutron star? The distinction matters, not just for classification, but for physics itself. Neutron stars are governed by equations of state that describe how matter behaves at ultra-high densities. If a neutron star could exist at nearly 3 solar masses, our understanding of the strong nuclear force, the fundamental force that binds quarks and gluons into neutrons and protons, would need to be revised. On the other hand, if XTE J1650-500 was a black hole, then it stood as the smallest known one, sitting delicately on the edge of gravitational collapse. Even more intriguingly, later studies suggested that the black hole in XTE J1650-500 might be spinning incredibly fast, close to the speed of light. This spin was inferred from the X-ray spectrum emitted by the accretion disk. In particular, researchers looked at the iron K-alpha line, a spectral signature emitted by iron atoms near the inner edge of the disk. The shape and broadening of this line can reveal how close the disk extends to the event horizon. In XTE J1650-500, the broadening suggested that the disk extended very close to the black hole itself, implying that it was spinning rapidly, pulling spacetime around with it like a cosmic whirlpool. A fast spin has profound implications. It means the black hole has angular momentum, which affects how matter falls into it, and how much energy can be extracted from the system. Some physicists even argue that rapidly spinning black holes could, in theory, act as engines for exotic processes, perhaps even powering relativistic jets or forming the backbone of high-energy astrophysical phenomena. For such a small black hole to spin so fast was another surprise, a twist in an already complex puzzle. But there's more. In addition to its physical properties, XTE J1650-500 also became a testbed for studying quasi-periodic oscillations, QPOs, subtle flickers in X-ray brightness that repeat at nearly regular intervals. QPOs are thought to originate in the innermost regions of the accretion disk, near the event horizon itself. These oscillations offer a rare glimpse into the dynamics of matter orbiting in the strongest gravitational fields imaginable. Studying QPOs allows scientists to probe the warping of spacetime, test aspects of general relativity, and even investigate how black holes interact with magnetic fields. In XTE J1650-500, the QPOs added yet another layer of complexity, suggesting that even this small black hole behaved like its more massive cousins in terms of energetic variability and emission patterns. The scientific debate surrounding XTE J1650-500 continues to this day. Its small mass remains controversial, partly because black holes are notoriously difficult to weigh accurately. We can't see them directly. We only infer their presence from the motion of nearby stars or the radiation from infalling gas. Every estimate comes with uncertainties, assumptions about distances, angles, and orbital parameters. Some astrophysicists have argued that the actual mass of XTE J1650-500 might be slightly higher than initial estimates suggested. Others believe it may yet hold the title of the lightest black hole known. Regardless of its final mass, XTE J1650-500 remains a cornerstone object in the study of compact astrophysical systems. It challenges boundaries, forces re-examinations, and invites deeper exploration of one of nature's most extreme phenomena. In doing so, it embodies the essence of scientific discovery, not a loud proclamation, but a quiet mystery that demands attention. And perhaps that is the most compelling thing about it. In a universe filled with supermassive black holes that weigh billions of solar masses, XTE J1650-500 is a cosmic whisper, a subtle suggestion that the universe still harbors secrets in the smallest of places. It reminds us that size is not the only measure of importance. Sometimes, the smallest things can raise the biggest questions. Of all the black holes ever discovered, XTE J1650-500 holds a particularly compelling place in astrophysical research due to its remarkably small mass, which flirts with the very boundary of what can be considered a black hole. Its existence raises deep questions about the lower mass limit of black hole formation, the end stages of stellar evolution, and the precise definition of these cosmic enigmas. Nestled approximately 11,000 light-years away in the constellation Era, this celestial object was first discovered by NASA's Rossi X-ray Timing Explorer, XTE, satellite in 2001. From the moment of its detection, the scientific community was captivated, not only because of its classification as an X-ray binary system but also because of the uncanny properties it exhibited, particularly in its mass. When our XTE first recorded the outburst from XTE J1650-500, it was seen radiating intense X-rays, characteristic of a black hole siphoning material from a companion star. The system consists of a stellar mass black hole and a low-mass companion star locked in a gravitational tango. As matter spirals inward from the companion into the black hole's accretion disk, it heats up to millions of degrees and emits high-energy X-rays. It's these emissions that first alerted scientists to the object's presence. What made this particular binary system stand out, however, was the unusual timing and spectral properties of its X-ray emissions, suggesting something far more peculiar was at play beneath the surface. The initial X-ray data prompted a flurry of activity among astronomers, who employed a variety of ground-based and space-based telescopes to peer deeper into the object's nature. Through careful spectroscopic observations, particularly with the European Southern Observatory's Very Large Telescope, VLT, and other high-resolution instruments, researchers were able to extract key parameters about the system's mass and orbital characteristics. The most shocking revelation was the mass of the black hole itself, estimated at around 3.8 solar masses. This figure, while above the maximum mass a neutron star can support before collapsing, was incredibly close to that threshold, making XTE J1650-500 a candidate for the smallest known black hole at the time. This placed XTE J1650-500 in a gray area of stellar evolution. Standard astrophysical models suggest that neutron stars, the dense remnants of supernova explosions, can exist up to around 2.5 to 3 solar masses. Beyond this limit, gravity overwhelms all forms of pressure-resisting collapse, and the object becomes a black hole. But if XTE J1650-500 truly has a mass as low as 3.8 solar masses, it lies just over that line. This blurs the distinction between neutron stars and black holes, compelling researchers to question whether there's an unbroken continuum between the two or a sharp dividing line. This mass gap region, typically considered to exist between about 2.5 and 5 solar masses, had few confirmed residents, making this discovery a vital data point in the study of compact object formation. As astronomers continued their investigation, they observed rapid X-ray variability in the emission from XTE J1650-500, especially in the form of quasi-periodic oscillations, QPOs. These oscillations, which appear as periodic flickers in the X-ray light curve, provide a unique window into the inner accretion disk just outside the event horizon. For XTE J1650-500, the presence of high-frequency QPOs in the 250 Hz range strongly supported the interpretation that it harbors a black hole. These frequencies correspond to the motion of matter in the innermost stable circular orbit, ISCO, around the black hole, allowing scientists to place constraints on both the mass and spin of the compact object. Perhaps one of the most fascinating aspects of XTE J1650-500's observational history lies in its iron K-alpha emission line. Using XMM Newton and Chandra X-ray observatories, researchers detected a broad and skewed iron emission line in the X-ray spectrum, a feature indicative of extreme relativistic effects in the region close to the black hole. The profile of this line suggested that the inner accretion disk was extending very close to the event horizon, a sign that the black hole is spinning rapidly. If true, this high spin rate would allow matter to orbit closer before plunging in, modifying the observable properties of the disk and enhancing the intensity of X-ray emissions due to frame dragging and gravitational redshift. All of this evidence converged to solidify the black hole interpretation of XTE J1650-500, even though its mass is tantalizingly low. But the implications of this low mass go far beyond classification. The question arises, how did such a small black hole form? Was it the remnant of a supernova explosion from a relatively low-mass progenitor star? Or did it form through some exotic, less understood process such as the collapse of a failed supernova or accretion-induced collapse of a neutron star? Each possibility has significant ramifications for our understanding of stellar evolution and the life cycles of massive stars. The more we learned about XTE J1650-500, the more it challenged our theoretical frameworks. If such low-mass black holes can exist, then it necessitates a reconsideration of core collapse supernova models. Current models suggest that black holes typically form from progenitor stars with masses greater than 20 times that of the Sun, which should yield black holes significantly larger than 5 solar masses. So either our models are missing some important piece of physics, or we are witnessing a rare class of black hole that formed under extraordinary conditions. Additionally, the existence of such a compact black hole implies the potential for many more similar objects to be lurking undetected in our galaxy. Their feeble accretion flows too dim to reveal their presence. Another hypothesis that gained traction was that XTE J1650-500 could be the result of a neutron star that accumulated enough mass through accretion from its companion to surpass the Tolman, Oppenheimer, Volkoff limit, the upper mass limit for a stable neutron star. In this scenario, once the critical threshold was crossed, the neutron star would have collapsed into a black hole, leaving behind a compact remnant of unusually low mass. If this mechanism is valid, it implies a pathway for black hole formation independent of direct supernova core collapse, further complicating the taxonomy of compact stellar remnants. On a cosmological level, objects like XTE J1650-500 act as laboratories for testing general relativity under extreme conditions. The space-time curvature in the vicinity of a black hole, particularly one with a rapidly spinning event horizon and a narrow mass profile, allows physicists to probe relativistic effects such as time dilation, gravitational redshift, and frame dragging. The iron line emissions observed from this system, when modeled correctly, can help refine our measurements of black hole spin, which in turn provides clues about the black hole's formation history and the angular momentum of its progenitor star. The implications for gravitational wave astronomy are equally significant. If small black holes like XTE J1650-500 are more common than previously believed, they may contribute to the population of compact object binaries whose mergers generate gravitational waves detectable by observatories like LIGO and Virgo. The detection of such low-mass mergers could validate or refute the existence of the mass gap and shed light on the underlying stellar physics that governs compact object formation. In fact, the continuing observations of gravitational wave events may already hint at similar mass ranges, although disentangling the precise masses involved remains an intricate challenge. Meanwhile, the continued study of XTE J1650-500 and similar systems sharpens the tools and models astronomers use to study distant X-ray binaries. By comparing it to other low-mass black hole candidates like GRO J0422+32 or 4U1543-47, scientists can begin to outline the broader population characteristics of these elusive objects. How common are black holes in the 3 to 5 solar mass range? Do they arise preferentially in certain types of binary systems? What evolutionary pathways are necessary to give rise to them? Each new data point nudges the field closer to understanding the true diversity of black hole formation. Further complicating the picture is the role of accretion feedback and radiation pressure in systems like XTE J1650-500. The X-rays we observe from such systems aren't just passive emissions, they actively influence the dynamics of the accretion disk, the rate of inflow, and even the mass loss from the companion star. This feedback loop creates a dynamic environment in which matter and energy interact in complex, nonlinear ways. Simulations suggest that radiation pressure could alter the inner disk structure, leading to state changes in the black hole's emission pattern, and possibly accounting for the transitions observed between high soft and low hard X-ray states during outbursts. XTE J1650-500 is far more than just a statistical outlier or a curiosity in the black hole zoo. It is a window into the extreme, a cosmic puzzle that forces astrophysicists to push the boundaries of their theories and confront the unknown with sharpened tools and open minds. Every flicker in its X-ray signature, every skewed emission line in its spectrum, and every whisper of gravity it radiates through space-time brings us closer to unraveling one of the universe's most enigmatic phenomena: the birth, nature, and limits of black holes. As researchers delve deeper into the study of XTE J1650-500, they found themselves at the crossroads of some of the most critical questions in astrophysics. The system's unique characteristics did not just present a mystery about one black hole, it potentially exposed a broader, systemic gap in our understanding of how stellar remnants evolve and interact. This singular object, a cosmic pinprick in the grand canvas of the galaxy, now served as a challenge to theoretical models and a guidepost for future observation campaigns. One of the more intriguing facets of the investigation into XTE J1650-500 was its companion star. In X-ray binary systems, the nature of the companion star can offer critical clues about the evolutionary path that led to the current configuration. The companion in this case is thought to be a low-mass star, possibly a late-type dwarf with less than half the Sun's mass. Observations in the optical band suggested that the star is not highly luminous, indicating a long period of mass transfer where it has been gradually losing material to the black hole via Roche-Lobe overflow. This process of mass exchange is responsible for fueling the black hole's accretion disk and producing the X-ray luminosity that made XTE J1650-500 observable in the first place. The orbital period of the binary system is another detail of enormous importance. The black hole and its companion complete an orbit roughly every 7.6 hours, a relatively short time that implies close proximity. Such tight orbits usually result from an extended period of angular momentum loss, likely due to magnetic braking or gravitational radiation. The evolution of these binaries over millions to billions of years leads to increasingly tighter orbits, until the companion star eventually spills material into the black hole's gravity well. This constant stripping of mass can prolong the active X-ray phase of the system, which is how objects like XTE J1650-500 are detected and studied. However, the process is not one-directional in terms of complexity. As the black hole feeds, the inner regions of the accretion disk can become so hot and dense that new physical regimes emerge. For instance, the matter in the inner disk can reach relativistic speeds, up to half the speed of light, creating effects like beamed emission and relativistic Doppler boosting. The intense gravitational field of the black hole also means that time dilation and lensing become dominant factors. Photons emitted near the event horizon may take curved paths, allowing astronomers to effectively see the far side of the disk as though it were face-on. This warping of space and time is not only a spectacular confirmation of general relativity, but also a tool for measuring the properties of the black hole itself. Perhaps even more captivating are the efforts to measure the spin of XTE J1650-500, a task fraught with technical challenges but rich in scientific payoff. Spin is the least understood of the three basic properties of a black hole: mass, charge, and spin, and in astrophysical black holes, charge is generally negligible. Spin, however, affects everything from the shape of the event horizon to the dynamics of the accretion disk and the potential for jet formation. Observations suggest that XTE J1650-500 could be spinning near the maximum allowed by the laws of physics, a curved black hole teetering on the edge of stability. Such a rapid spin hints at either a high angular momentum at birth or a prolonged period of accretion that has spun up the black hole over time. The spin measurement is primarily inferred through the analysis of the broadened iron K-alpha line, which reveals how close the innermost edge of the accretion disk lies to the event horizon. The closer this inner edge is, the higher the spin must be to support stable orbits that close to the black hole. In the case of XTE J1650-500, the iron line appears highly broadened and skewed, supporting a high-spin interpretation. The implications of this are manifold. If the black hole was born spinning rapidly, it challenges our understanding of angular momentum conservation in supernovae. If, instead, the spin is a result of accretion, it provides insight into the efficiency and longevity of mass transfer in low-mass X-ray binaries. Beyond the spectral and timing analyses, there is another layer of complexity to consider: the environment in which XTE J1650-500 formed. Our galaxy, the Milky Way, is dotted with regions of active star formation, as well as stellar graveyards where the remnants of past generations of stars reside. XTE J1650-500 is believed to be part of the galactic disk population rather than the halo, implying it formed relatively recently in cosmic terms, within the last few billion years. This suggests that progenitor stars capable of forming low-mass black holes may not be rare, and that XTE J1650-500 could be representative of a larger, yet undetected population. If this is the case, then surveys using next-generation X-ray observatories could uncover many more such systems. Missions like Rosetta, Athena, and the proposed Lynx X-ray Observatory aim to survey the sky with unprecedented sensitivity and resolution, potentially revealing dozens or even hundreds of faint X-ray binaries harboring low-mass black holes. Each discovery would help fill in the statistical gaps that currently plague our understanding of the compact object mass distribution. Meanwhile, the theoretical community continues to wrestle with the implications of XTE J1650-500. Some astrophysicists propose that the mass gap between neutron stars and black holes may be an artifact of observational bias. Historically, we have been more likely to detect either high-mass black holes or relatively massive neutron stars because their observational signatures, such as gravitational wave events or luminous X-ray emissions, are more prominent. As instruments become more sensitive, the lower end of the black hole mass spectrum might begin to populate more densely, gradually erasing the mass gap or redefining its boundaries. Another possibility is that the formation of such small black holes is inherently rare and dependent on fine-tuned initial conditions, such as metallicity, rotation rate, and binary interaction history. High metallicity stars tend to lose more mass through stellar winds, reducing the core mass and possibly preventing black hole formation. On the other hand, stars in low metallicity environments might retain enough mass to form black holes without passing through the neutron star phase. The specific combination of initial mass, composition, and binary interaction that leads to a low-mass black hole might be infrequent, but not impossible. In the grander scheme of cosmic evolution, understanding the demographics of black holes like XTE J1650-500 informs not just stellar evolution theory but also galaxy formation models and chemical enrichment histories. Black holes play a role in redistributing energy through their jets and winds, influencing star formation and their surroundings. Even a relatively small black hole like XTE J1650-500, in the right environment, could exert a measurable influence on its local interstellar medium, particularly during outbursts when accretion rates peak and powerful winds or jets may be launched from the inner disk. Indeed, while no relativistic jets have been definitively associated with XTE J1650-500, there have been hints of radioactivity during outburst phases, suggesting that the system may exhibit jet-like behavior. The detection of such jets would be another point in favor of its black hole nature, since jets are typically launched via the Blandford-Znajec mechanism or other magnetic processes that rely on the presence of an event horizon and a spinning compact object. If jets are present, even intermittently, it further distinguishes XTE J1650-500 from any possible neutron star analogues. In terms of public perception and scientific storytelling, XTE J1650-500 has quietly carved out a niche as an object of deep scientific value. Unlike the famous supermassive black holes at the centers of galaxies or the merging giants detected by gravitational wave observatories, this humble, stellar mass black hole doesn't generate headlines. Yet, for researchers, it offers a trove of insights that could reshape our understanding of what black holes are, how they form, and how they influence the universe around them. Its legacy is also secure in the annals of observational astronomy. As new missions scan the sky, XTE J1650-500 serves as a benchmark, a test case against which new candidates can be compared. Whether its mass proves to be an outlier or a herald of a broader population remains to be seen. But one thing is certain: it has already expanded the horizon of what is considered possible in the realm of compact objects. As studies into XTE J1650-500 advanced, it became increasingly clear that this seemingly unremarkable black hole, lacking the attention of its more famous cosmic cousins, was far more significant than initially thought. For one, its mass estimate, hovering at around 3.8 solar masses, thrust it directly into the contentious mass gap region that had long been debated among astronomers and astrophysicists. If this estimate held true, it would serve as direct evidence that black holes can exist at the lower end of the stellar mass spectrum, bridging the previously observed chasm between the most massive neutron stars and the least massive black holes. The importance of this discovery cannot be overstated. For years, the existence of the mass gap between 2.5 and 5 solar masses posed a significant challenge to conventional stellar evolution models. Neutron stars, the remnants of collapsed massive stars that aren't quite massive enough to form black holes, typically max out around 2.2 to 2.5 solar masses due to the Tolman-Oppenheimer-Volkoff limit. Above this limit, the neutron degeneracy pressure that supports the star against gravitational collapse fails, theoretically leading to the formation of a black hole. However, black holes discovered via X-ray binaries and gravitational wave observations from LIGO and Virgo have usually been significantly heavier, often beginning at 5 solar masses or more. This discrepancy gave rise to the notion of a mass gap, suggesting that something fundamental about stellar evolution or black hole formation prevented the creation of objects in this narrow mass range. Theories proposed everything from supernova explosion mechanics, fallback accretion, and parent stability phenomena as possible explanations. If XTE J1650-500 was indeed a black hole with a mass below 5 solar masses, it would challenge those explanations or force them to account for exceptions. What made XTE J1650-500 especially intriguing was the potential for precision measurements of its mass through multiple methods. The most direct method involved analyzing the motion of its companion star. By observing Doppler shifts in the spectrum of light emitted from the star, researchers could track its orbit and thereby infer the gravitational pull it experienced from the black hole. From this, the so-called mass function could be derived, offering a lower limit on the black hole's mass based on the system's inclination and other orbital parameters. However, one of the major sources of uncertainty in such measurements is the system's inclination angle, the tilt of the orbital plane relative to our line of sight. A system viewed edge-on yields more reliable mass estimates than one viewed face-on, since the Doppler shifts are more pronounced. In XTE J1650-500's case, early estimates suggested a high inclination angle, which would support a lower black hole mass, reinforcing its candidacy as the smallest known black hole. Later observations sought to refine this estimate further, using everything from optical photometry to X-ray eclipses and variability studies. Another pathway to understanding XTE J1650-500 came from the study of its accretion disk and X-ray emissions. During periods of increased accretion, when matter from the companion star flowed more rapidly into the black hole, the system entered an outburst phase, characterized by elevated X-ray luminosity and changes in its spectral state. These outbursts allowed researchers to study the black hole's emission profile in both the soft and hard X-ray bands. Spectral fitting models helped determine the temperature of the inner accretion disk and the radius at which emission peaked. The proximity of this inner disk radius to the black hole itself offered clues about the event horizon and spin. One of the landmark moments in the study of XTE J1650-500 came with the analysis of the relativistically broadened iron K-alpha line in its spectrum. This particular emission line, generated when iron atoms in the inner accretion disk are excited by high-energy radiation and re-emit photons, carries the imprint of extreme gravitational and relativistic effects. The shape of the line, Its broadening, redshifting, and skewing tells a story about the spacetime near the black hole. For XTE J1650-500, this line appeared unusually distorted, suggesting that the inner accretion disk extended very close to the event horizon. This implied not only a rapidly spinning black hole but also one of very low mass, as more massive black holes typically push the innermost stable circular orbit farther out. But even more fascinating was how this single system could potentially help resolve deeper questions in astrophysics. If XTE J1650-500's black hole were truly spinning near the maximum allowed by general relativity, it would provide a unique laboratory for testing predictions of Einstein's theory in the strong field regime. Frame dragging, for instance, where spacetime itself is pulled along by the rotating mass, becomes significant in such conditions. This leads to phenomena such as lens-stirring precession, which affects the orientation of the accretion disk and modulates the X-ray emission over time. Measuring these subtle effects could allow astronomers to test aspects of general relativity that are otherwise inaccessible. Then there's the question of how such a rapidly spinning, low-mass black hole could have formed in the first place. If it was born spinning this fast, then the core collapse supernova that birthed it must have preserved a tremendous amount of angular momentum. This challenges existing models, which usually assume that magnetic braking and mass loss during the progenitor star's life reduce angular momentum significantly before collapse. On the other hand, if the black hole was spun up through prolonged accretion from the companion star, then XTE J1650-500 must have been a persistent, long-lived binary with a stable transfer of matter over millions of years. Either scenario raises compelling questions about the history of the system and the broader population of such binaries in the galaxy. Moreover, if systems like XTE J1650-500 are more common than previously thought, it raises the possibility that we've been underestimating the number of low-mass black holes in the Milky Way. Traditional detection methods, biased toward more massive or more luminous systems, may have missed an entire population of silent black holes, those that accrete very slowly or lie dormant for most of their existence. If even a small fraction of these systems undergo periodic outbursts like XTE J1650-500, wide-field X-ray monitoring missions could eventually uncover them. Their discovery would help fill in the missing pieces of the stellar mass compact object distribution and offer a more complete census of black holes in our galaxy. XTE J1650-500 has also sparked renewed interest in black hole formation models. One of the leading questions is whether black holes form via a prompt collapse, where the core of a dying star implodes directly into a black hole, or through a fallback scenario, where a neutron star forms briefly but then accretes enough mass to collapse further. A low-mass black hole like the one in this system would support the latter model, especially if it can be shown that the progenitor was only marginally massive. This would imply a more nuanced boundary between neutron stars and black holes, potentially influenced by factors like rotation, metallicity, and binarity. The role of metallicity, in particular, is gaining attention. High metallicity stars tend to lose more mass through winds during their lifetimes, leading to smaller cores and possibly neutron star formation. Low metallicity stars retain more mass and are thus more likely to form black holes. If XTE J1650-500's progenitor came from a low metallicity environment, this might explain the formation of such a small black hole. Tracing the chemical history of the region surrounding XTE J1650-500 could therefore offer additional clues, linking black hole demographics with galactic chemical evolution. What's remarkable is how XTE J1650-500, a faint, seemingly unremarkable point in the sky, has become a Rosetta Stone for black hole research. It has triggered new observational campaigns, inspired refinements in theoretical models, and even prompted the development of novel instrumentation designed to probe black holes with greater precision. Future missions like the European Space Agency's Athena or NASA's proposed Lynx Observatory could study such systems in unprecedented detail, unraveling mysteries that have persisted for decades. Even as we gaze further into the cosmos with tools like the James Webb Space Telescope and gravitational wave detectors, objects like XTE J1650-500 remind us that profound revelations often come not from the grandest, most dramatic events, but from the quiet persistence of anomalies, those stubborn data points that refuse to fit the curve. In its silence, XTE J1650-500 has spoken volumes. And with each passing year, it promises to reveal even more. The path of understanding XTE J1650-500 is, in many ways, a microcosm of our evolving comprehension of stellar death, gravitational collapse, and the incredible extremes of the universe. While its low mass defies easy categorization, its behavior, interactions, and measurable properties continue to challenge the boundaries of what we know about black holes. One compelling aspect of this system lies in its companion star. XTE J1650-500, like many X-ray binaries, is part of a stellar duet, where one member is a normal star and the other is the black hole. This relationship is essential for making the black hole detectable in the first place. Without the luminous emissions generated as the black hole siphons matter from its companion, XTE J1650-500 would be invisible against the backdrop of space. The dynamics of this binary interaction reveal much about the mass of the black hole, the orbital period of the system, and the life cycle of the pair. In this specific system, the orbital period is extremely short, just about 7.7 hours, meaning the companion star and black hole are locked in a tight, almost frantic dance. The proximity of the stars implies that the black hole is actively pulling material from its companion, forming an accretion disk in the process. This disk spirals inward, heating up to millions of degrees and emitting high-energy X-rays that flare into space. These X-rays are our window into the system, offering insights into everything from the nature of the matter flowing into the shape and size of the gravitational abyss at the center. What's especially captivating is the temporal variability of these emissions. XTE J1650-500 doesn't simply emit a constant stream of X-rays. Instead, it pulsates and fluctuates, showing dramatic shifts in brightness and energy over time. These variabilities fall into categories known as quasi-periodic oscillations, QPOs, which are among the most intriguing phenomena associated with accreting black holes. QPOs are thought to arise from changes in the structure of the accretion disk, resonant frequencies caused by orbiting matter, or even the effects of space-time warping near the event horizon. In the case of XTE J1650-500, the presence of high-frequency QPOs has led researchers to speculate about the inner edge of its accretion disk lying close to the innermost stable circular orbit. This supports the idea that the black hole is rapidly spinning, which would allow matter to orbit closer before plunging into the singularity. Moreover, the frequency of these oscillations might offer a way to probe the properties of the black hole itself, including its mass and spin, with unprecedented precision. In fact, the frequencies observed in XTE J1650-500 have been among the highest ever recorded, providing fertile ground for theoretical modeling and computational simulation. The disk itself is a marvel of physics, an environment where magnetic fields twist and tangle, radiation pressure battles gravity, and temperatures soar to unimaginable extremes. As matter spirals inward, it passes through different stages of heating and compression, emitting across the electromagnetic spectrum. X-ray observations from missions like RXTE and Chandra have provided snapshots of these processes in action, revealing everything from the temperature gradients of the disk to the mechanisms of energy dissipation. But XTE J1650-500 is not just about emissions and orbits, it's also about silence. For the majority of its time, the system remains in a quiescent state, with very little activity detectable from Earth. These quiet periods are just as important as the outbursts, as they allow astronomers to study the baseline characteristics of the system, including the spectrum of the companion star and the precise orbital parameters. During quiescence, the glare of the accretion disk fades, making it easier to detect subtle features of the system that would otherwise be drowned out. Another extraordinary dimension to XTE J1650-500's story is its potential role in gravitational wave astronomy. While gravitational waves have mostly been associated with the mergers of compact objects, black holes colliding with black holes, neutron stars with neutron stars, or combinations thereof. Systems like XTE J1650-500 offer a glimpse into the types of progenitor binaries that might one day produce such cataclysmic events. If, over millions or billions of years, this binary system evolves such that the companion collapses into another compact object, the resulting merger could send ripples through space-time detectable by observatories like LIGO, Virgo, or CAGRA. Even if a merger is not in its future, the gravitational influence of the black hole on its companion and on nearby space offers a way to test the predictions of Einstein's general relativity. Subtle shifts in the timing of orbits, changes in the spectral line profiles, and even the bending of light near the system's event horizon are all potential tests of gravitational theory. In the years ahead, missions such as the Laser Interferometer Space Antenna, LISA, may be able to detect even more subtle gravitational signatures from systems like XTE J1650-500. It's also worth contemplating the broader population of black holes in our galaxy. XTE J1650-500 may be unique in its mass and spin, but it is unlikely to be entirely alone. If such low-mass black holes exist, they may be hiding in plain sight, waiting for the occasional accretion event to make them visible. Upcoming all-sky surveys in the X-ray and optical bands may uncover hundreds or thousands of such systems, offering a statistical foundation for understanding black hole formation pathways and their distribution across the Milky Way. In this regard, XTE J1650-500 serves as a harbinger of discovery, a benchmark system that challenges our theories and guides the design of future experiments. Its discovery in 2001 may have been serendipitous, but its continued study is deliberate, purposeful, and transformative. It is shaping our understanding of compact objects, binary evolution, and the extreme physics of accretion and relativistic gravity. The interplay of theoretical astrophysics, observational astronomy, and high-energy physics in the study of XTE J1650-500 also highlights the interdisciplinary nature of modern science. Researchers must draw from a wide array of disciplines: fluid dynamics, nuclear physics, quantum mechanics, and relativistic theory, to piece together the story of this system. And as our computational power increases, simulations of systems like XTE J1650-500 will grow ever more detailed, enabling virtual reconstructions of its life cycle from stellar birth to black hole formation and beyond. Indeed, questions abound. How did the progenitor star of XTE J1650-500 evolve? Did it go supernova, or collapse quietly into a black hole? What was the role of mass transfer in shaping the final mass and spin of the black hole? How stable is the current mass transfer rate? What long-term evolutionary pathway does this system follow? Could it someday host a double compact object? These are not idle musings. They are the front lines of current astrophysical research, and XTE J1650-500 stands at their center. As scientists delve deeper into the structure and behavior of XTE J1650-500, another fascinating aspect begins to emerge: the notion of black hole evaporation. While currently more a subject of theoretical physics than empirical observation, Hawking radiation, the hypothetical process by which black holes slowly lose mass, adds a new dimension to our understanding of black holes, especially ones with extremely low mass like XTE J1650-500. Stephen Hawking predicted in 1974 that black holes aren't entirely black. They emit radiation due to quantum effects near the event horizon. For stellar mass black holes, this radiation is so weak that it's essentially undetectable with current instruments. But if XTE J1650-500 really is the smallest known stellar mass black hole, then its evaporation rate, though still minuscule, would be slightly more pronounced than that of larger black holes. This introduces questions about the ultimate fate of such objects over cosmic timescales. Could low-mass black holes like this one evaporate faster than their larger counterparts? Could future technology allow us to detect the infinitesimal glow of Hawking radiation? These speculative yet thrilling ideas propel researchers to examine every bit of XTE J1650-500's characteristics, from its X-ray flux to its gravitational pull, in hopes of refining theoretical models. And what's perhaps most striking is how such a seemingly small object, a black hole only a few times more massive than our Sun, can lead to such monumental questions about time, space, entropy, and the limits of observation itself. Beyond its physical properties, XTE J1650-500 is also a narrative about technological progress. The very act of detecting and interpreting its data required the integration of high-resolution X-ray satellites, ground-based optical telescopes, and sophisticated data analysis software. Instruments like our XTE Rossi X-ray Timing Explorer, which first observed its flare-up, allowed astronomers to detect millisecond-scale variations in its emissions. Chandra X-ray Observatory and XMM Newton followed up with high-precision spectral data, revealing the detailed structure of its emissions and giving rise to models of its accretion disk and spin. It's worth contemplating that without these orbiting eyes, peering into the high-energy universe, XTE J1650-500 would remain an unseen mystery. And while the stars shine bright, much of this story unfolds in darkness, in the invisible stretches of space where gravity overcomes even light. The name black hole is more than poetic. It encapsulates the paradox of these cosmic giants, unseen, yet undeniable. The gravity of XTE J1650-500, its ability to shape its companion's orbit, to pull in matter and release high-energy photons, all betray its otherwise hidden nature. This is one of the many reasons black holes captivate the public imagination. They are secrets in the sky, exposed only through their effects on the things around them. One can't help but be struck by the age of the system. Stars that collapse into black holes typically do so at the end of lifespans measured in millions to billions of years. XTE J1650-500, then, is ancient, perhaps as old as the Milky Way itself. Its progenitor star would have burned bright and fast, likely a massive star that lived a short, violent life before undergoing gravitational collapse. And now, eons later, it remains, a ghost of stellar fury, feeding slowly on its partner, whispering secrets of the early universe through X-ray pulses. And those whispers carry far. The light we see from XTE J1650-500 today began its journey tens of thousands of years ago, traveling through the interstellar medium, past stars and dust clouds, to eventually be captured by our telescopes. In that sense, we aren't just observing a distant system, we are looking back in time, receiving an ancient message encoded in energy. Every flare, every dip in brightness, every spectral line is a note in the ongoing symphony of cosmic evolution. What makes this story even more profound is the possibility that XTE J1650-500 might not be the smallest black hole. It may be the smallest we've found so far, but the cosmos is vast and largely unexplored. There could be smaller black holes, hidden away in dim corners of galaxies, waiting for their companion stars to spill matter and light into their grasp. Future observatories, both ground-based and spaceborne, might detect them. Projects like the Vera C. Rubin Observatory and missions like Athena will revolutionize our ability to detect faint, transient sources, and it's entirely likely that many more low-mass black holes will be uncovered in the coming decades. And as we discover more, we refine our theories. For example, some astrophysicists have suggested that what we observe as a low-mass black hole might instead be a new kind of exotic object, perhaps a quark star, or a gravistar. These hypothetical objects arise from extreme physics beyond our current understanding and may mimic many of the signatures of black holes. Could XTE J1650-500, with its perplexingly small mass, actually be something else? The debate continues, and with it, the boundaries of science are pushed further. Then there is the public perception of black holes, often seen as monstrous, all-consuming entities. But XTE J1650-500 defies this caricature. It is small, precise, and far from apocalyptic. Its interactions are measured in solar masses and hours, not galactic destruction. Yet in its tiny frame, it encapsulates the full majesty of gravitational collapse and relativistic motion. It is both violent and elegant, destructive and illuminating. In its gravitational well, particles orbit at relativistic speeds, time dilates, and space curves into unknowable dimensions. There's also the philosophical weight of such discoveries. If something as small and compact as XTE J1650-500 can still warp space and time to such an extent, what does that say about the universe we live in? What does it mean to live in a cosmos where invisible objects control visible matter, where the past is ever present in the form of traveling light, and where the very laws of nature must bend around singularities? In this way, the study of XTE J1650-500 isn't just science. It's a kind of cosmic meditation. It demands we think beyond human timescales, beyond human senses, beyond Earth. It invites us into a universe of extremes, where mass collapses, time slows, and light ceases to be the fastest thing we know. And in doing so, it makes the familiar strange and the unknown a little more knowable. What lies ahead for this enigmatic system? The companion star will continue to orbit, its atmosphere slowly eroded by the tidal pull of the black hole. The accretion disk may flare again, lighting up in a new outburst, revealing new patterns and variations. Instruments on Earth and in orbit will keep watching, cataloging every photon. And over time, the system may evolve, growing quieter, dimmer, until even the accretion stops and the black hole is left in silent orbit with a white dwarf or neutron star companion, the embers of a once dynamic duo. And yet, even then, its story won't end. In the far future, long after humanity is gone, long after our sun has died and our planet is dust, XTE J1650-500 may still be orbiting silently in the dark, a gravitational monument to the processes that shaped it. Its continued existence into the deep future is a sobering and poetic thought. XTE J1650-500, this small, silent black hole, may well outlive the galaxies themselves. As stars fade, galaxies collide, and cosmic structures dissolve into cold, dark entropy. Black holes like XTE J1650-500 could persist. Slowly, ever so slowly, they will evaporate through Hawking radiation, shedding mass at a rate that stretches across trillions of years. But until that unimaginably distant end, it remains a sentinel of gravity, a relic of stellar death, and a monument to the universe's most extreme phenomena. This reality forces us to reevaluate the scale on which we comprehend time and permanence. Human history, from the earliest civilizations to today's space age, has spanned but a few thousand years. And yet, in the lifetime of a black hole, even a relatively young one like XTE J1650-500, this period is less than a flicker. Our entire existence is dwarfed not just by its mass, but by its endurance. These are not merely objects of scientific curiosity, they are eternal fixtures in a cosmos where nearly everything else is fleeting. And we must also appreciate how fragile our view of such entities really is. It's only because we've built space-based telescopes with sensitive X-ray detectors and collaborated across countries and disciplines that we can even talk about black holes like XTE J1650-500. Our ability to study such an object rests on precise coordination, advanced physics, powerful computing, and relentless curiosity. The precision required to determine the mass of the black hole, to model the spectrum of its X-ray emissions, and to infer the nature of its companion star, all of it represents the very peak of human technological achievement. At the same time, this capability comes with humility. Because even as we decipher the mechanics of this system, questions multiply. How did such a small black hole form? Was it the remnant of a highly specific stellar collapse scenario? Did it lose mass through previous interactions, or was its progenitor simply not massive enough to yield a typical black hole? If it's indeed as small as estimated, around 3.8 solar masses, then it forces us to refine the boundary between neutron stars and black holes. The commonly accepted theoretical lower limit for black hole mass, based on the Tolman, Oppenheimer, Volkoff limit, is around 2 to 3 solar masses. XTE J1650-500 rests just above that threshold, making it a prime candidate for exploring what lies at the very edge of known physics. Even more compelling is the way its spin might shape our understanding of black hole formation. Spin is not just a rotational property, it's a fossil record of the black hole's birth and evolution. If XTE J1650-500 is spinning near the speed of light, it could mean the collapsing star had an immense angular momentum, or that the black hole was spun up through prolonged accretion. Measuring that spin isn't easy, but when it's possible, it reveals insights into the history of stellar death and binary dynamics. And consider the incredible energy environment around such a system. The region near the event horizon is so extreme that particles spiral inward at relativistic speeds, heated to millions of degrees, emitting X-rays powerful enough to cross vast cosmic distances. These emissions, often variable, offer a direct view into the feeding habits of the black hole. They also help us test theories of accretion, magnetic field interactions, and the properties of relativistic jets. Though XTE J1650-500 hasn't shown strong jet activity like some other systems, its outburst still carries clues about what causes black holes to produce jets in the first place. Is it tied to spin? To magnetic field alignment? To the state of the accretion disk? These are the mysteries that turn astronomers into detectives. Observations are matched against simulations, predictions are tested against light curves, and slowly, incrementally, the story of the black hole becomes clearer. Yet, the deeper we look, the more questions we encounter, questions that stretch beyond physics into the realm of metaphysics. What is the nature of singularity at the core of a black hole like XTE J1650-500? Is it a point of infinite density, or is there some quantum limit that prevents true singularities from forming? Could spacetime break down in a way we don't yet understand? Some physicists suggest that information, once thought lost to black holes, is preserved in ways we've yet to grasp, perhaps in the event horizon, or even in subtle correlations within the Hawking radiation itself. If that's true, then every particle that falls into XTE J1650-500 is not truly gone, but encoded in the very fabric of its existence. In this sense, the black hole becomes not just a gravitational object, but a cosmic archive, holding secrets of the matter it has consumed. And what of its companion star? Without it, XTE J1650-500 would be invisible, a dormant black hole with no fuel, no light, no signature. But because of the binary relationship, we see the signs of activity. We can study the orbit, calculate mass functions, determine inclination angles, and map the gravitational choreography of the system. This is not just a black hole, it's a dance between two stars, one visible, one hidden, their relationship defined by attraction, accretion, and slow, inexorable change. Over time, the companion star will change too. As it loses mass, it may evolve off the main sequence. Its structure will shift, its outer layers may be stripped, and what's left could be a compact remnant, a white dwarf or neutron star. That would mark a new era for the system, a binary with two dead stars, one of them an invisible singularity, locked in mutual orbit until external forces, perhaps galactic tides, disrupt their dance. And so we return to the black hole itself. In the end, XTE J1650-500 is more than just a mass, a spin, and a coordinate in the sky. It's a node in a vast network of cosmic interactions. It's a product of stellar evolution, a testbed for relativistic physics, a beacon of X-ray emissions, and a reminder of the power and mystery that lies hidden in the dark. It's a story that spans billions of years and reaches across thousands of light years to whisper in the ears of our detectors. It tells us something fundamental, that the universe is full of secrets, and we are just beginning to learn how to listen. As we continue to probe the nature of XTE J1650-500, we are reminded of how much is still left unknown. The mystery of black holes and their influence on their surroundings is far from resolved. While we have made great strides in understanding how black holes form, how they behave, and what they can teach us about the fabric of space and time, we have only scratched the surface. Each new discovery, like XTE J1650-500, only deepens the complexity of the universe and forces us to rethink old theories, while encouraging new lines of inquiry. The nature of XTE J1650-500 forces a reconsideration of our theoretical frameworks, especially when it comes to the formation of black holes and binary systems. Unlike the more massive stellar mass black holes, which typically form from the collapse of massive stars. XTE J1650-500 represents a special case. It sits near the boundary where a neutron star and a black hole could merge in terms of mass. This ambiguity raises intriguing possibilities for the transition between a neutron star and a black hole. In typical stellar collapse models, once a star surpasses a certain mass threshold, around 8 to 10 solar masses, it will undergo a supernova, leading to either the formation of a neutron star or a black hole, depending on the remaining mass of the core. If the remnant mass is too high, it will collapse into a black hole. If it's not, it becomes a neutron star. The case of XTE J1650-500 suggests that the boundary is not as clear-cut as once thought, and systems like this are likely more common than we previously believed. Some stellar remnants, especially those in binary systems, may live in this murky space between neutron stars and black holes. The smaller mass of XTE J1650-500 also has significant implications for the understanding of the maximum size of black holes. Theoretically, the smallest possible black hole should have a mass of at least a few times that of our Sun, and yet, XTE J1650-500 pushes that limit, suggesting there may be far more varieties of black holes out there that we have yet to discover. As for the black hole's companion star, the relationship between them is critical to understanding how this system functions. Binary systems like XTE J1650-500 typically involve the transfer of mass from the companion star to the black hole via the process of accretion. In this case, XTE J1650-500 is an X-ray binary system, where the black hole pulls material from its companion, generating intense X-ray radiation. As the material spirals inward toward the black hole, it forms an accretion disk, a rotating disk of matter heated to extremely high temperatures as it approaches the event horizon. These disks emit X-rays that provide us with vital information about the black hole's properties, such as mass, spin, and accretion rate. However, the discovery of a black hole like XTE J1650-500, which is relatively small by black hole standards, also underscores the role of mass transfer in binary systems. Over time, the black hole will continue to draw matter from the companion star, and the nature of this transfer will evolve. As the companion star loses mass, its core will shrink, and it will likely evolve into a white dwarf or neutron star, marking the end of its stellar evolution. In the long run, the fate of this binary system will depend on the black hole's ability to continue pulling mass from its companion, and whether the black hole will be able to increase its mass over time. The discovery of XTE J1650-500 is also important for advancing our understanding of the gravitational wave revolution. The detection of gravitational waves from merging black holes has opened an entirely new window into the universe, allowing scientists to study the most extreme objects in the cosmos in ways that were once unimaginable. Although XTE J1650-500 has not been associated with a gravitational wave event, at least not yet, the system remains a strong candidate for future observation as gravitational wave detectors become more sensitive. As the technology to detect these waves improves, systems like XTE J1650-500 could provide key insights into the collision and merging of small black holes, offering a glimpse into the inner workings of black hole binaries. Moreover, the study of XTE J1650-500 provides an important test for the theory of Hawking radiation. This theoretical form of radiation, which was proposed by physicist Stephen Hawking in 1974, suggests that black holes are not entirely black but emit radiation due to quantum effects near the event horizon. While the effects of Hawking radiation are exceedingly faint for large black holes, they might be more detectable in smaller black holes like XTE J1650-500. This gives astronomers the potential to test quantum gravity theories in the most extreme conditions imaginable. Beyond that, black holes like XTE J1650-500 help us understand how matter behaves under extreme conditions. The gravitational pull near the event horizon is so powerful that even light cannot escape, and it distorts space and time in ways that challenge our understanding of physics. As such, studying small black holes offers us a chance to explore fundamental questions about the nature of gravity, space, and time itself. We are pushed to the limits of our understanding of physics as we attempt to reconcile the equations of general relativity with quantum mechanics. And yet, the mysteries surrounding XTE J1650-500 remain only partially unraveled. We have seen how black holes challenge our deepest intuitions about the universe, pushing the boundaries of science and philosophy alike. Every new observation brings us closer to a more complete picture, but the full story of these cosmic giants remains elusive. Their incredible power, mysterious nature, and enduring presence offer a tantalizing glimpse into the heart of the universe, a place where the normal rules of physics seem to break down, and where the secrets of reality are locked away in singularities, just beyond our reach. XTE J1650-500 is far more than just another black hole in a distant galaxy. Its relatively small size, unique formation history, and ongoing interactions with its companion star place it at the forefront of astrophysical research. Every new detail we uncover about this system provides us with vital clues about the origins and nature of black holes, the intricacies of stellar evolution, and the fundamental workings of the cosmos itself. As we continue to probe the universe with ever more advanced tools and techniques, systems like XTE J1650-500 will remain a key focus of investigation, reminding us that the universe is still full of surprises, and that there is always more to learn in our quest to understand the very nature of space, time, and existence. The fascinating nature of XTE J1650-500 does not stop at its small size, or its peculiar place in the family of black holes. The system's discovery itself reveals a deeper mystery about our observational capabilities and the potential for finding smaller black holes than we ever thought possible. In essence, every new finding in the study of black holes has the potential to overturn what we believe we know about the universe. XTE J1650-500 is not just important because of its size, but because it acts as a cosmic laboratory, a natural environment where we can study the extreme conditions that give rise to one of the most enigmatic objects in existence. One of the most compelling aspects of studying small black holes, like the one in XTE J1650-500, is that they offer us a unique perspective on gravitational theories. For decades, black holes were thought to be defined by a relatively simple mass boundary. A black hole either had a mass that was many times that of the Sun, or it didn't. But XTE J1650-500 challenges that, showing us that black holes may come in a far wider range of sizes than we've previously anticipated. This brings with it an important philosophical and scientific question. If we can find a small black hole like XTE J1650-500, might there be even smaller black holes scattered throughout the universe? Perhaps black holes that were previously undetectable because they are not only small in mass but also faint in terms of radiation emissions. The study of black holes, and in particular, the study of small ones, can tell us much about how stellar remnants form in binary systems. As mentioned before, stellar mass black holes are typically formed when massive stars undergo supernova explosions, leaving behind a collapsed remnant. The remnant's mass, energy, and dynamics all play key roles in determining whether it will become a neutron star or a black hole. The case of XTE J1650-500 might suggest that the process by which black holes form in binary systems is much more nuanced than we once believed. In the dense, gravitationally intense environment of a binary system, the black hole's formation might take a slightly different course compared to the traditional models of isolated stellar collapse. Furthermore, the material that the black hole pulls from its companion star through the process of accretion can potentially have a significant impact on the black hole's mass and growth over time, adding complexity to the understanding of how black holes evolve. Additionally, as the study of smaller black holes such as XTE J1650-500 expands, so too does the need to better understand the properties of the accretion disks around them. These disks, made of hot gas and other debris drawn in by the black hole's immense gravitational pull, can provide some of the most detailed data we have about the inner workings of a black hole. The behavior of these disks, including their temperature, the rate of material being drawn in, and the interaction between the gas and the magnetic fields could all be dramatically different in smaller black holes. XTE J1650-500, being one of the smallest black holes discovered to date, may help us unlock further secrets about how accretion disks behave in a way that we have not yet fully understood, particularly in the context of smaller, less massive systems. But why do we care about small black holes at all? It's easy to become enamored with the massive, supermassive black holes that dominate the centers of galaxies, or the black holes that create dazzling displays of X-rays as they consume stars and binary systems. But smaller black holes offer us the opportunity to study black hole physics in a far more accessible context. They allow us to test theories and predictions that we may not be able to test with their larger counterparts. Furthermore, smaller black holes are more likely to exist in systems with less intense gravitational fields, making them ideal candidates for examining how these objects interact with the rest of the universe in more subtle ways. When we explore the future of XTE J1650-500, we must consider the possibility that more discoveries like it will come. As more telescopes are launched into space and more sophisticated detection techniques come online, the universe will likely reveal more of its secrets. The study of small black holes like XTE J1650-500 will become more and more significant as we search for the elusive, missing link between neutron stars and black holes, a link that could unlock even greater mysteries about the nature of space, time, and gravity. In a sense, black holes, particularly smaller black holes, represent one of the most profound paradoxes in the study of astrophysics. They are the ultimate cosmic enigma, challenging our understanding of physics and the very nature of reality. The discovery of XTE J1650-500 has opened a new chapter in this quest for knowledge, and it serves as a reminder that the universe is still full of surprises. We continue to discover new and unexpected objects, and each of these discoveries offers us a new way of thinking about the universe and our place within it. As more data is collected on XTE J1650-500 and other small black holes, it's not just astrophysicists who are affected by the findings. The implications of these discoveries extend beyond the realm of pure science and into the realm of philosophy. Black holes, in many ways, challenge our perception of reality itself. They represent points in space where the known laws of physics break down, where time and space become warped beyond comprehension. As we study these objects, we are forced to confront fundamental questions about the nature of existence. Are black holes truly gateways to another dimension, as some theories suggest? Or are they simply the ultimate manifestations of gravitational collapse, where the laws of physics as we understand them cease to function? One of the most intriguing aspects of studying black holes like XTE J1650-500 is that they provide a natural testbed for exploring the limits of our understanding of the universe. The extreme environments near a black hole's event horizon, where gravity is so intense that not even light can escape, offer a unique opportunity to test the predictions of general relativity and quantum mechanics. As we continue to explore these enigmatic objects, we may eventually come to realize that the universe operates according to rules we have yet to fully comprehend. Perhaps XTE J1650-500 and other small black holes are simply a stepping stone toward uncovering a deeper, more fundamental understanding of the fabric of reality itself. The fascinating part of black holes like XTE J1650-500 is not just the groundbreaking potential they offer in refining theoretical models, but also in the kind of new insights they can offer into the structure and evolution of our universe. As astrophysicists continue to observe and analyze the properties of such objects, there is the underlying hope that we can answer some of the most profound questions in the field of cosmology. How did the universe begin? What are the true nature and fate of space and time? Are black holes the keys to unlocking the hidden laws that govern the cosmos? In a universe where many objects are challenging to study, small black holes like XTE J1650-500 can also be viewed as an opportunity to dig deeper into the physical properties of the universe in ways we couldn't with larger or more distant black holes. Their relatively small mass and more accessible location allow us to better analyze their behavior, both in isolation and in relation to the environments they inhabit. Understanding how such objects function is not just a theoretical exercise, it's a key component in piecing together the cosmic puzzle of how celestial bodies are born, grow, and evolve over time. In the context of XTE J1650-500's discovery, one of the core challenges that remains is how black holes interact with their surroundings. We know that they have a profound impact on the stars, gas, and other objects that fall within their gravitational grasp, but the specifics of these interactions remain murky. XTE J1650-500 provides us with a unique window into this realm. The black hole's proximity to a companion star in a binary system means that it is engaged in a dynamic exchange of mass and energy, a process that allows us to observe how black holes grow and how they influence their immediate environments. The binary system's interaction also offers an excellent case study for testing and refining models of how such systems evolve over time, leading us closer to an understanding of how massive black holes and galaxies form. Moreover, the study of XTE J1650-500 is essential for understanding the role of black holes in the larger structure of galaxies. As we have seen with larger supermassive black holes, these objects play a key role in shaping the dynamics of galaxies, influencing everything from the formation of stars to the growth of galactic structures. But in the case of smaller black holes like XTE J1650-500, it's not just about their impact on the galaxy's overall structure, it's also about their influence on the very building blocks of matter. Their gravitational pull shapes the surrounding material, bending light, warping space-time, and even influencing the paths that nearby objects follow. While our knowledge of black holes in general has advanced significantly over the past few decades, XTE J1650-500 holds a special place in the ongoing pursuit of understanding the behavior of stellar mass black holes. The combination of its relatively small mass and its location within a binary system makes it an ideal candidate for further study. Its discovery is a reminder that the universe is far more complex than we initially believed, and that there are still many unknowns that scientists must confront in order to unravel the deepest mysteries of the cosmos. In particular, the small mass of XTE J1650-500 raises important questions about the lower bounds of black hole mass. Before this discovery, it was widely believed that black holes formed from stellar remnants needed to exceed a certain mass threshold to become black holes in the first place. The discovery of XTE J1650-500 suggests that black holes may be able to form even from the remnants of less massive stars. This revelation not only broadens our understanding of black hole formation but also opens up new avenues of research in the search for other small black holes in the universe. Perhaps there are even more of them hiding in plain sight, undetected by conventional observation methods. In fact, the ongoing study of XTE J1650-500's accretion disk and the way it interacts with its companion star could provide invaluable insight into the formation and evolution of black holes across a wide range of masses. The intricate dance of gas and stellar matter around the black hole in this binary system is rich with scientific potential, from helping us better understand the specifics of how matter behaves in extreme gravitational fields to refining our theoretical models of black hole physics. And as technology continues to improve, the study of XTE J1650-500 will only become more promising. Modern telescopes and observational tools, such as the Chandra X-ray Observatory, are capable of revealing fine details of black holes and their accretion disks in ways that were once unimaginable. These advances are crucial in the study of small black holes, which require precise, high-resolution measurements to understand their properties. As these instruments capture more data, we will be able to observe the behavior of black holes like XTE J1650-500 with unprecedented clarity, further enhancing our understanding of the universe. Looking further ahead, the study of smaller black holes like XTE J1650-500 also has the potential to shed light on more speculative, but no less exciting areas of research. Some theoretical physicists have speculated that small black holes could hold the key to understanding quantum gravity, an area of physics that seeks to reconcile the principles of quantum mechanics with the general theory of relativity. This is no easy task, as these two foundational theories are at odds with one another in many ways. But if black holes, particularly small ones, can provide a natural laboratory for testing the limits of both theories, then XTE J1650-500 could play a pivotal role in unraveling one of the greatest mysteries in physics today. The discovery of XTE J1650-500 is a landmark moment in the study of black holes, offering a glimpse into a new frontier of astrophysics. Its small size and fascinating properties serve as a reminder that the universe is full of surprises, and that our understanding of black holes is still very much in its infancy. This black hole, along with others like it, will continue to challenge scientists to rethink the conventional wisdom about stellar mass black holes and to push the boundaries of what we know about the most extreme objects in the universe. XTE J1650-500, while small in mass compared to its larger counterparts, represents an essential piece of the puzzle in understanding the formation, growth, and behavior of black holes. Its existence forces us to reconsider previous assumptions about the boundaries of black hole masses, and opens the door to further discoveries that could change everything we know about these mysterious cosmic entities. As scientists continue to study XTE J1650-500 and other similar objects, we move one step closer to unlocking the true nature of black holes, and by extension, the fabric of the universe itself. The importance of XTE J1650-500 cannot be overstated, as it lies at the intersection of several pivotal areas of modern astrophysical research. As we begin to understand how black holes form, grow, and interact with their environment, objects like XTE J1650-500 offer us the chance to explore the intricacies of spacetime itself. One of the remarkable aspects of black holes is their ability to warp spacetime around them, creating regions where the laws of physics, as we understand them, break down. This warping is most pronounced near the event horizon, the boundary beyond which nothing, not even light, can escape. While much of our understanding of black holes has been shaped by the study of more massive supermassive black holes at the centers of galaxies, the discovery of stellar mass black holes like XTE J1650-500 adds an entirely new layer to our understanding. It underscores the idea that black holes of various sizes exist across the cosmos, each with its own unique set of characteristics and behaviors. By studying these objects, we can begin to unravel the details of how black holes form and evolve, shedding light on their role in the broader cosmological context. Moreover, the interplay between the black hole and its companion star in the binary system of XTE J1650-500 provides a rare opportunity to observe the physics of accretion in action. The companion star's material is gradually pulled into the black hole's gravitational grip, forming an accretion disk that heats up as it spirals inward. This process releases an enormous amount of energy, particularly in the form of X-rays, which we can detect using specialized space telescopes. By studying the properties of this X-ray emission, we can glean crucial information about the black hole's mass, spin, and the composition of its accretion disk. What makes XTE J1650-500 even more intriguing is that it sits on the edge of a theoretical threshold. In many ways, it represents a bridge between stellar mass black holes and intermediate mass black holes, which are still largely hypothetical. Intermediate mass black holes are believed to exist between the 100–1000 solar mass range, which is larger than the typical stellar mass black holes but significantly smaller than the supermassive black holes at the centers of galaxies. The existence of objects like XTE J1650-500 provides valuable insights into how these intermediate mass black holes might form, and whether they can play a role in the formation of even larger black holes in the centers of galaxies. This discovery has also spurred renewed interest in the search for other small black holes throughout the universe. As observational technology improves, we are now able to probe regions of space that were previously beyond our reach. XTE J1650-500, with its relatively nearby location, has become an ideal target for further study using advanced observational techniques. Future missions will likely focus on gathering more detailed data about the black hole's behavior and its interactions with the surrounding material, helping us to further refine our understanding of these enigmatic objects. There is still much to learn about the specific mechanisms that drive the growth and evolution of black holes, particularly those in binary systems. In the case of XTE J1650-500, the black hole's gravitational pull causes it to feed on the companion star, stripping away material from its outer layers. This material, as it gets closer to the event horizon, forms a hot, rotating disk that emits intense radiation. Observing this process in real time is a key aspect of black hole research, as it allows scientists to test predictions made by the theory of general relativity. One of the primary challenges in understanding these systems lies in measuring the dynamics of the accretion disk. In a binary system, the material being pulled toward the black hole is not only influenced by the black hole's gravity, but also by the motion of the companion star. The gravitational interaction between the two objects can cause the material in the accretion disk to become turbulent, creating variations in the X-ray emission that we observe. By carefully analyzing the X-ray data collected from XTE J1650-500, scientists can gain a better understanding of the forces at play within the accretion disk and how these forces affect the overall behavior of the system. Another intriguing aspect of XTE J1650-500 is the possibility that it could help resolve some of the long-standing mysteries in black hole physics. One such mystery revolves around the spin of black holes. According to general relativity, black holes can rotate at incredible speeds, with some potentially spinning so fast that their event horizons would become distorted. The study of XTE J1650-500 could provide valuable insights into the spin rate of black holes in binary systems, helping us to understand how angular momentum is transferred between the black hole and its companion star. The data collected from XTE J1650-500 has the potential to reveal important clues about the larger-scale structure of black holes in the universe. In particular, astronomers are keen to understand how black holes interact with their environments, shaping the formation of stars, galaxies, and even entire clusters of galaxies. By observing how small black holes like XTE J1650-500 influence their surroundings, we can begin to piece together the larger cosmic picture, one that includes not only the black holes themselves but also the galaxies and star systems they inhabit. Looking ahead, the study of black holes like XTE J1650-500 will continue to push the boundaries of our knowledge. As we develop more advanced observational tools and refine our theoretical models, we will gain a deeper understanding of these mysterious objects and their role in the universe. The ongoing exploration of black holes in all their forms, whether stellar mass, intermediate mass, or supermassive, offers the promise of uncovering the deepest secrets of the cosmos. For now, XTE J1650-500 remains a fascinating and valuable piece of the puzzle, offering scientists a glimpse into the heart of one of the most enigmatic phenomena in astrophysics. As we venture further into the study of black holes, we are reminded of the vastness and complexity of the universe. Black holes like XTE J1650-500 may be small in terms of their mass, but they are still incredibly powerful and influential. Their ability to warp space-time, affect their surrounding environment, and challenge our understanding of physics makes them invaluable objects of study. Every discovery about these objects brings us one step closer to unlocking the mysteries of the universe, and XTE J1650-500 is no exception. What makes XTE J1650-500 so compelling is not just its status as the smallest known black hole, but the way it challenges our assumptions about the universe. It forces us to reconsider how black holes form, how they grow, and how they interact with their surroundings. And as we continue to observe and study this fascinating object, we may just uncover more profound insights that could reshape our understanding of space, time, and the very fabric of reality itself. As we continue to explore the intricacies of black holes like XTE J1650-500, we find that their study does not just expand our knowledge of the cosmic phenomena themselves but also illuminates some of the most fundamental aspects of the universe. To understand these celestial objects, we must delve into the concepts of gravity, space-time, and the limits of human knowledge. black holes challenge our perception of what is possible in the universe, especially when considering their mysterious ability to warp the very fabric of space and time. One of the most fascinating aspects of XTE J1650-500 is its proximity to Earth. Located around 10,000 light-years away in the constellation Era, it is one of the closest stellar mass black holes we have discovered. This relatively short distance, in astronomical terms, provides a unique opportunity to study the behavior of a black hole in great detail. Thanks to this proximity, scientists have been able to observe the system more directly than they could with more distant black holes, which may be too faint or distant to detect in high resolution. The black hole in XTE J1650-500, like all black holes, is a region in space where gravity is so strong that nothing, not even light, can escape its pull. The event horizon, which marks the boundary of this region, is not a physical surface but rather an imaginary line, beyond which anything that crosses it is irrevocably drawn inward toward the singularity, the infinitely dense point at the center of the black hole. Despite the fact that we cannot observe the singularity itself, due to the event horizon, scientists can infer its existence and study the surrounding region, where intense gravitational and electromagnetic forces are at play. One of the primary ways we observe black holes like XTE J1650-500 is through the X-rays emitted by the material in the accretion disk as it spirals toward the event horizon. As material from the companion star falls into the black hole, it is heated to extreme temperatures due to the immense gravitational forces acting on it. This process creates intense X-ray radiation, which can be detected by space-based telescopes such as NASA's Chandra X-ray Observatory or the European Space Agency's XMM Newton. By studying the properties of this X-ray emission, astronomers can gain insights into the structure of the accretion disk, the mass and spin of the black hole, and the dynamics of the system as a whole. This process of accretion also provides a window into the way in which black holes influence their surroundings. As material is drawn into the black hole, it releases energy that can affect the companion star, potentially altering its evolution. The energy released from the accretion disk can heat up surrounding gas clouds, triggering new star formation or causing the gas to be ejected from the system in powerful outflows. These interactions between black holes and their environment are a critical area of study, as they have broad implications for our understanding of galactic evolution and the role black holes play in the larger structure of the universe. In the case of XTE J1650-500, the mass of the black hole is believed to be around 3.8 solar masses, which places it firmly within the category of stellar mass black holes. Stellar mass black holes typically form when massive stars reach the end of their life cycle and collapse under the force of gravity, creating a singularity surrounded by an event horizon. However, the exact processes by which these black holes grow and evolve over time are still not fully understood. It is believed that black holes like XTE J1650-500 are able to grow by accreting material from their companion stars, though it remains unclear whether this growth is steady or whether there are periods of intense activity followed by more quiescent phases. XTE J1650-500 provides an important opportunity to study this growth process in detail. As the material from the companion star is drawn into the black hole, it forms a disk that radiates intense energy. By observing the variability in this radiation, scientists can learn about the dynamics of the accretion disk, the processes by which material is transferred from the companion star to the black hole, and the ways in which the black hole's growth might influence the system as a whole. This kind of detailed observation is crucial for understanding the long-term evolution of black holes and their role in shaping the galaxies in which they reside. One of the key questions that astronomers hope to answer by studying XTE J1650-500 is how black holes of different sizes form and evolve. Most of the black holes we observe are either stellar mass black holes, which typically range from a few solar masses to around 10 to 15 solar masses, or supermassive black holes, which reside at the centers of galaxies and have masses ranging from millions to billions of solar masses. But black holes in the intermediate mass range, those with masses between 100 and 1,000 solar masses, are much rarer and more difficult to detect. Their existence is predicted by current theories of black hole formation, but we have very few direct observations of such objects. The discovery of XTE J1650-500 provides a crucial piece of the puzzle. While it is not in the intermediate mass range, it is very close, and studying it could help us better understand how black holes of this size form and evolve. This information could help bridge the gap between stellar mass black holes and intermediate mass black holes, shedding light on the pathways through which black holes grow and accrete material. In the long term, this research may lead to a deeper understanding of how supermassive black holes form in the early universe and how they influence the galaxies around them. Additionally, XTE J1650-500 offers insights into the so-called black hole spin, one of the most intriguing aspects of black hole physics. Black holes are believed to possess angular momentum, or spin, which can affect the behavior of the material around them. The spin of a black hole is an important factor in determining the shape of its event horizon and the dynamics of its accretion disk. In fact, the spin can have a profound effect on the way material falls into the black hole, potentially causing the black hole to spool or twist the fabric of spacetime around it. Recent studies have suggested that measuring the spin of a black hole can provide important clues about the nature of the material in its accretion disk and the way the black hole interacts with its environment. By studying the X-ray emission from XTE J1650-500, astronomers hope to determine the spin rate of the black hole and explore how this spin affects the behavior of the system. In particular, they are interested in understanding whether the spin rate of XTE J1650-500 is consistent with the predictions of general relativity, and how it compares to other black holes of similar mass. The study of XTE J1650-500 also holds implications for our understanding of the broader cosmic environment in which black holes exist. The discovery of such a small black hole challenges the conventional wisdom about black hole populations and their role in galaxy formation. It suggests that black holes of various sizes are more common than we once thought, and that their interactions with the surrounding environment can play a key role in shaping the evolution of galaxies and star systems. The continued observation and study of objects like XTE J1650-500 will be crucial for refining our models of galaxy formation and understanding the ways in which black holes influence the cosmos. As the field of black hole research continues to evolve, we are likely to see even more surprising discoveries. With advancements in technology and observational techniques, we may uncover new black holes of varying sizes, each with its own unique characteristics and mysteries. These objects will continue to challenge our understanding of the universe and push the boundaries of astrophysics, offering us glimpses into the deepest recesses of spacetime and the very nature of gravity itself. The case of XTE J1650-500 exemplifies the power of modern astrophysics to explore the unknown. Even the smallest black holes, like this one, can reveal profound insights into the workings of the universe, from the behavior of matter under extreme conditions to the nature of space and time. As we continue to study these enigmatic objects, we inch closer to unlocking the secrets of the cosmos, understanding not only how black holes form and evolve, but also their role in the larger cosmic dance. In the vastness of space, every discovery, no matter how small, brings us one step closer to unraveling the mysteries of the universe. In the case of XTE J1650-500, the fact that it is potentially the smallest known black hole places it at the center of numerous questions surrounding the formation, growth, and evolution of these cosmic giants. While we have long known that black holes exist, our understanding of their specific characteristics, such as mass, spin, and size, is still evolving. With objects like XTE J1650-500, we gain a better understanding of the diversity within black hole populations, especially among stellar mass black holes. The size of a black hole is directly related to its mass. However, the mass isn't the only factor that shapes a black hole. Its spin, for example, can influence the dynamics of the system it inhabits, including how matter falls into it, how it emits energy, and how it interacts with its environment. In XTE J1650-500, the size of the black hole is not just an interesting fact about its physical dimensions, it is tied to the fundamental question of how these objects behave, and what they can teach us about the fabric of space and time. The mass of a black hole, which is often measured in terms of solar masses, is a crucial characteristic in determining the type of black hole we are dealing with. Stellar mass black holes typically have masses between 3 and 15 times that of the Sun, and XTE J1650-500 is thought to fall into this category. These black holes are the remnants of massive stars that have collapsed under their own gravity after exhausting their nuclear fuel. The death of a massive star often results in the formation of a black hole, and as the star's mass increases, so does the resulting black hole. However, the mass is not the only factor that defines a black hole. It is also its spin and the accretion disk surrounding it. The spin of a black hole can be thought of as the angular momentum it possesses. Black holes are known to rotate, and their spin can be detected by studying the way light and radiation behave near the event horizon. The faster a black hole spins, the more extreme the gravitational forces are around it. This has far-reaching implications for both our understanding of black holes and how we study them. The spin of a black hole is crucial for understanding the behavior of the accretion disk. As matter spirals toward the black hole, it forms a disk of hot gas and dust that emits radiation. The intense gravitational pull of the black hole causes this matter to accelerate, and as it nears the event horizon, it becomes increasingly heated, emitting high-energy radiation that can be detected by telescopes. The spin of the black hole can affect how this matter behaves. A rapidly spinning black hole can cause the material in the accretion disk to be compressed more tightly, which increases the intensity of the radiation emitted. In XTE J1650-500, researchers are particularly interested in measuring the spin of the black hole. By studying the X-ray emission from the accretion disk, they hope to determine how fast the black hole is spinning and gain insight into the dynamics of the system. This information could provide valuable clues about the early stages of black hole formation and the processes that govern the growth of black holes over time. The role of accretion is essential to understanding the life cycle of a black hole like XTE J1650-500. As the black hole pulls material from its companion star, this material accumulates in the accretion disk and forms a region of intense energy release. This energy is not just emitted as light and X-rays but can also have profound effects on the surrounding gas and dust, heating them up and causing them to glow with intense radiation. The dynamics of the accretion disk and the way it interacts with the black hole provide valuable insight into how black holes grow and how they influence their environment. XTE J1650-500 is part of a larger class of objects known as X-ray binaries. These systems consist of a black hole and a companion star, with the black hole accreting material from the star. The X-ray emissions observed from these systems provide valuable information about both the black hole and its companion. In the case of XTE J1650-500, the companion star is a relatively massive star that is in close orbit with the black hole. The material from this star is drawn toward the black hole, forming the accretion disk and emitting X-rays in the process. Understanding the interaction between the black hole and its companion star is essential for understanding how black holes accrete material and grow over time. As material falls into the black hole, it carries away energy, which can have significant consequences for the companion star. In some cases, the black hole's influence on its companion star can lead to the star's eventual destruction. However, in other cases, the star may continue to orbit the black hole for millions or even billions of years, slowly losing mass as it is consumed by the black hole. The mass of the black hole in XTE J1650-500 plays an important role in the dynamics of the system. With a mass of around 3.8 solar masses, it is a relatively small black hole compared to some of the more massive black holes that have been discovered. However, even small black holes have an enormous gravitational pull. The strength of the gravitational field near the event horizon of XTE J1650-500 is so great that it can influence the motion of the companion star and cause the material in the accretion disk to accelerate to speeds close to the speed of light. This high velocity leads to the intense X-ray emission that we can observe from Earth. While XTE J1650-500 is not the only stellar mass black hole to be discovered, its size and behavior make it an important object of study. It provides an opportunity to study the properties of black holes with masses at the lower end of the stellar mass range, which are typically more difficult to detect and study. By understanding black holes like XTE J1650-500, we can gain insight into the processes by which black holes form, grow, and interact with their surroundings. In addition to the scientific implications, the study of XTE J1650-500 has important consequences for our understanding of the larger universe. Black holes like XTE J1650-500 play a crucial role in shaping the structure of galaxies and in driving the processes that govern the evolution of stars. The interactions between black holes and their environment, including the accretion of material from companion stars and the emission of radiation, have far-reaching effects on the surrounding space. By studying these processes, we can gain a deeper understanding of how galaxies evolve and how the most extreme objects in the universe shape the cosmos. Furthermore, XTE J1650-500 is part of a broader effort to understand the diverse population of black holes in the universe. While stellar mass black holes like XTE J1650-500 are relatively common, black holes with masses in the intermediate range are much rarer. The study of XTE J1650-500 can provide crucial information about the formation and evolution of black holes in this mass range, which is an important step toward understanding how supermassive black holes form in the early universe. The quest to understand black holes like XTE J1650-500 is also tied to the broader search for the fundamental laws of physics that govern the universe. Black holes, with their extreme conditions of space-time curvature and gravitational forces, are natural laboratories for testing the predictions of Einstein's theory of general relativity. By studying the behavior of black holes, scientists hope to uncover new insights into the nature of space, time, and gravity. In particular, the study of the spin and mass of black holes may provide clues about the behavior of spacetime near the event horizon and the possibility of new physics beyond general relativity. As we continue to observe and study XTE J1650-500, new technologies and advancements in our observational capabilities will allow us to gather even more detailed data. With the next generation of space telescopes, we may be able to directly image the event horizon of black holes like XTE J1650-500, offering an unprecedented view of these enigmatic objects. This will allow us to refine our models of black hole behavior and further expand our understanding of the most extreme objects in the universe. XTE J1650-500 is a remarkable and significant discovery in the study of black holes. As one of the smallest known stellar mass black holes, it offers a unique window into the behavior of black holes in the universe and the processes by which they form and grow. Its study provides insights into the dynamics of accretion, the nature of black hole spin, and the interactions between black holes and their companion stars. Furthermore, it contributes to our broader understanding of the evolution of galaxies and the fundamental laws of physics that govern the universe. As we delve deeper into the study of XTE J1650-500, we must consider the broader implications of black holes in general and their role in astrophysics. Stellar mass black holes like XTE J1650-500 provide us with a tangible connection to some of the most fundamental questions in physics, especially regarding the nature of spacetime, gravity, and the limits of our current understanding of quantum mechanics. These objects challenge the very fabric of reality, as they represent the ultimate extreme in mass, gravity, and density, where the usual laws of physics break down. The discovery of such a small black hole pushes the boundaries of what we thought we knew about the mass limits of black holes. Traditionally, black holes formed from stellar collapse are thought to fall within a certain range of masses, typically between 3 and 15 solar masses for stellar mass black holes. XTE J1650-500, with a mass around 3.8 solar masses, is at the lower end of this spectrum, and this has profound implications for our understanding of how these objects form and evolve over time. Does this discovery suggest that stellar mass black holes can be even smaller than previously thought? Or does it imply that black holes in this mass range could have unique formation histories or processes that we have yet to fully understand? The study of XTE J1650-500 has also opened up new avenues for research into the ways in which black holes interact with their environments. We are only beginning to scratch the surface when it comes to understanding the intricate relationships between black holes and their companion stars. For example, how does the mass and spin of the black hole influence the transfer of material from the companion star to the accretion disk? Does the black hole's gravitational pull alter the orbit of the companion star in such a way that it triggers unusual phenomena, like the periodic emission of X-rays or the ejection of high-energy particles? One of the most exciting aspects of studying XTE J1650-500 lies in the potential to uncover clues about the nature of accretion disks and how they emit high-energy radiation. As matter spirals toward a black hole, it forms a disk of material that heats up due to the friction and gravitational forces at play. This heated material emits X-rays, and by studying these emissions, astronomers can gain insight into the properties of the black hole, including its mass, spin, and the behavior of the matter around it. XTE J1650-500 is particularly intriguing because it resides in a system where the interaction between the black hole and its companion star is relatively well understood. By studying the way in which the companion star's material is drawn into the black hole, we can learn more about the process of accretion and how it affects both the black hole and its environment. This process of accretion is one of the most important phenomena in astrophysics, as it not only provides insights into the growth of black holes, but also helps us understand the mechanisms behind the emission of X-rays and other high-energy radiation. In the case of XTE J1650-500, the material from the companion star is heated to extremely high temperatures as it spirals inward. This process releases an enormous amount of energy, which is emitted as X-rays that can be detected by telescopes on Earth. The study of these X-rays allows scientists to probe the conditions around the black hole and determine important properties like its mass and spin. These observations also provide insight into the behavior of matter under extreme gravitational forces, helping to refine our understanding of the nature of black holes and the forces that govern their behavior. One of the key challenges in studying black holes like XTE J1650-500 is the difficulty in directly observing the black hole itself. Black holes, by definition, do not emit light, making them invisible to traditional telescopes. Instead, we rely on indirect methods to study them, such as observing the X-ray emissions from the accretion disk or monitoring the motion of the companion star. The technology used to detect these emissions has improved significantly over the past few decades, with X-ray observatories like the Chandra X-ray Observatory providing detailed data on black hole systems like XTE J1650-500. While the technology for studying black holes has improved, challenges still remain. For instance, the accuracy with which we can measure the mass and spin of a black hole is still limited by the precision of our instruments and the complexity of the physical processes involved. In the case of XTE J1650-500, astronomers are working to refine their models of how matter behaves in the extreme environment near the black hole. This includes modeling the dynamics of the accretion disk, the interactions between the black hole and the companion star, and the emission of high-energy radiation. One fascinating aspect of studying black holes like XTE J1650-500 is the role they play in the larger context of the universe. Black holes, especially stellar mass black holes, are thought to be important contributors to the evolution of galaxies. The process of accretion, in which matter is drawn into the black hole, can influence the surrounding environment in profound ways. As the black hole feeds on its companion star, it releases energy in the form of X-rays and other radiation, which can affect the surrounding gas and dust, triggering the formation of new stars or altering the dynamics of the galaxy. In addition to their role in galaxy formation, black holes like XTE J1650-500 can also provide valuable clues about the formation and evolution of the universe itself. The study of black holes and their interactions with their environments can shed light on the fundamental forces that govern the cosmos, including the nature of gravity, space-time, and matter. By studying black holes at different stages in their evolution, scientists can gain insights into how these objects grow, evolve, and influence the broader universe over time. Another important aspect of studying black holes is the potential for testing the fundamental laws of physics. Black holes, particularly those like XTE J1650-500 that exist in relatively low-mass systems, offer an opportunity to test the predictions of general relativity and quantum mechanics under extreme conditions. The way in which matter behaves near the event horizon of a black hole, and the way in which it is affected by the black hole's gravitational field, can provide important insights into the nature of spacetime itself. By studying the properties of XTE J1650-500, scientists hope to test the limits of our understanding of these fundamental forces and uncover new insights into the nature of reality. The study of black holes is not just about answering questions about these enigmatic objects themselves, but also about understanding the broader workings of the universe. The extreme environments around black holes provide a unique laboratory for testing the laws of physics and probing the behavior of matter and energy in ways that are impossible to replicate on Earth. Black holes like XTE J1650-500 are natural laboratories for testing theories of gravity, space-time, and quantum mechanics, and their study may ultimately lead to a deeper understanding of the universe as a whole. As our ability to observe and study black holes improves, we can expect even more discoveries and breakthroughs in the years to come. Future space telescopes, such as the James Webb Space Telescope, will provide unprecedented views of the universe and allow us to study black holes and other extreme objects in greater detail than ever before. These advancements will continue to expand our knowledge of black holes, including those like XTE J1650-500, and will likely lead to new discoveries about the nature of space, time, and the fundamental forces of the universe. The study of XTE J1650-500 and other black holes like it holds the potential to answer some of the most profound questions in astrophysics. By continuing to explore these objects, we will gain new insights into the fundamental nature of the universe and the laws that govern it. And as our understanding deepens, we may uncover new mysteries and challenges that will drive the next generation of scientific discovery. The exploration of XTE J1650-500 not only opens the door to understanding the smallest known black holes, but it also allows us to contemplate the broader implications of their role in the universe. The sheer complexity of these objects, how they form, grow, and interact with their surroundings, pushes the boundaries of our scientific understanding. One of the most fascinating aspects of studying XTE J1650-500 is how this particular black hole challenges the current theories of stellar collapse and the formation of black holes. In the case of stellar mass black holes, the general assumption has always been that these objects form when massive stars exhaust their nuclear fuel, leading to a supernova explosion. The remnant core left behind after the explosion then collapses into a black hole. This process usually creates black holes with masses between 3 and 15 solar masses. However, the discovery of XTE J1650-500, with its smaller than expected mass of just around 3.8 solar masses, raises questions about the exact processes that govern the formation of black holes. Can a smaller black hole form from a star that isn't as massive as we thought? Or does this particular black hole represent a unique case, something we haven't fully accounted for in our current models? This question is significant not only because of the discovery of this small black hole but also because it challenges our understanding of stellar evolution. The mass of a black hole is directly linked to the properties of the star that formed it. A smaller black hole, like XTE J1650-500, suggests that the star that formed it might have undergone a different evolutionary path compared to the stars that typically form black holes. Could it be that certain stellar environments or chemical compositions lead to the formation of these smaller black holes? Or does the mass of the black hole indicate that XTE J1650-500 was formed through a different mechanism altogether, perhaps involving the merging of smaller stellar remnants, or the influence of surrounding gas and dust? Beyond the specific case of XTE J1650-500, this discovery has broader implications for our understanding of black hole formation in general. If black holes of this size are more common than previously thought, it could reshape the way we classify and study stellar mass black holes. It may lead to the discovery of a whole new population of black holes with smaller masses, previously undetected due to the difficulty in identifying them among the more common, larger black holes. Moreover, XTE J1650-500 invites us to reconsider the way we detect and observe black holes. Traditionally, black holes have been identified through their interactions with companion stars or through the detection of their accretion disks. However, the smaller the black hole, the less material it might be able to pull from its companion star, making it more challenging to detect. In the case of XTE J1650-500, its relatively faint X-ray emissions may have been one of the reasons why it remained undetected for so long. This underscores the importance of refining our observational techniques to detect more subtle signals from smaller black holes, which could lead to even more groundbreaking discoveries in the future. The study of XTE J1650-500 and other small black holes is also vital for understanding the concept of black hole binaries. In a black hole binary system, the black hole is in orbit with a companion star, and matter from the companion star is drawn toward the black hole. This process can result in the formation of an accretion disk, which emits X-rays and other forms of radiation that allow astronomers to study the black hole's properties. The interaction between the black hole and the companion star is crucial for understanding the dynamics of these systems. For example, how does the black hole's gravitational pull affect the motion of the companion star? How does the material from the star flow toward the black hole, and what happens to it as it spirals inward? These are fundamental questions that can only be answered through detailed study of black hole binaries like XTE J1650-500. Another intriguing aspect of studying black holes like XTE J1650-500 is the possibility of revealing new insights into the behavior of matter and energy under extreme conditions. The region surrounding a black hole, especially near its event horizon, is one of the most extreme environments in the universe. In these regions, gravitational forces are so intense that space-time itself is warped, and the laws of physics, as we understand them, no longer behave in the way we expect. This extreme environment provides a natural laboratory for testing the limits of our understanding of gravity, quantum mechanics, and the nature of space-time. XTE J1650-500's small mass also raises questions about the behavior of matter in the inner accretion disk. How does this relatively low-mass black hole manage to pull in material at the rate that we observe? Is there a unique process occurring in this particular system that leads to the efficient accretion of material, or is this a more general feature of smaller black holes? Understanding these processes could not only shed light on the behavior of black holes but also on the broader mechanics of accretion disks, which are fundamental to the way in which black holes interact with their surroundings. Furthermore, XTE J1650-500 may serve as a key to understanding the broader landscape of black hole physics and cosmology. By studying the masses, spins, and environments of black holes in more detail, astronomers can begin to piece together a more complete picture of how these enigmatic objects fit into the larger structure of the universe. How do black holes like XTE J1650-500 influence the formation and evolution of galaxies? What role do they play in the growth and dynamics of supermassive black holes at the centers of galaxies? These are questions that can only be answered by continuing to study black holes across a wide range of masses, from the stellar mass black holes like XTE J1650-500 to the supermassive black holes found at the heart of many galaxies. As the study of XTE J1650-500 progresses, new techniques and tools will become available to astronomers, allowing them to explore this intriguing system in even greater detail. Next-generation telescopes, such as the James Webb Space Telescope and the next generation of X-ray observatories, will enable astronomers to detect black holes with even greater sensitivity, potentially uncovering more small black holes that have thus far remained hidden. Additionally, advances in computational modeling and simulations will allow scientists to better understand the behavior of black holes and their interactions with their environments, providing new insights into the nature of these mysterious objects. While the discovery of XTE J1650-500 represents a significant breakthrough in our understanding of black holes, it is just one piece of the puzzle. The universe is filled with a vast array of black holes of all sizes and masses, each offering a unique opportunity to explore the most fundamental questions in physics. By continuing to study black holes, from the smallest stellar mass black holes like XTE J1650-500 to the largest supermassive black holes, we can gain a deeper understanding of the nature of space, time, and the forces that shape the universe. Ultimately, the study of XTE J1650-500 and other black holes represents the frontier of modern astrophysics. As we continue to push the boundaries of our knowledge, we may uncover even more surprising and perplexing discoveries about the universe, each one bringing us closer to unraveling the deepest mysteries of existence. From the behavior of matter near the event horizon to the fundamental forces that govern the cosmos, the journey of discovery is only just beginning. The mysteries surrounding XTE J1650-500 go beyond just its mass and size. As astronomers delve deeper into the complexities of this small black hole, they find that it offers crucial insights into the nature of accretion disks, relativistic jets, and how black holes interact with their environments. These phenomena, once thought to be characteristic only of larger black holes, are now found to also be a part of the small black hole ecosystem. One particularly exciting aspect of studying smaller black holes, like XTE J1650-500, is the fact that they challenge traditional models of black hole accretion. In larger black holes, the accretion disk, the swirling disk of gas and dust falling into the black hole, tends to be much brighter due to the vast amount of material being sucked in at high rates. However, in the case of XTE J1650-500, the lower mass of the black hole means that it pulls the material at a much slower rate, making the accretion disk far less luminous. This is especially intriguing because it offers astronomers the opportunity to study how black holes accumulate mass under lower energy conditions. Studying these disks in detail can help us understand how accretion works on different scales and under different conditions. The reduced luminosity of the XTE J1650-500 system does not mean that it is any less active or dynamic. Far from it. In fact, these lower mass black holes may behave quite differently than their larger counterparts. XTE J1650-500's relatively quiet accretion disk might not produce as many X-rays, but it does produce periodic bursts of radiation. These bursts are essential for understanding the timing and variability of black hole systems. Such variability is especially important because it reveals the dynamics within the innermost parts of the black hole's accretion disk and the inner regions of the black hole itself. The physics governing these bursts of radiation is still not entirely understood, making them an area of intense study for astrophysicists. Another significant area of interest with XTE J1650-500 is its potential to help us understand the role of relativistic jets. Jets are streams of matter that are ejected at nearly the speed of light from the regions surrounding black holes, and they have been observed in larger black holes. These jets are thought to be powered by the interaction between the black hole's magnetic field and the material in the accretion disk. In most systems, these jets are often linked to highly energetic environments where large amounts of matter fall into the black hole. For smaller black holes, however, the situation might be different. While smaller black holes like XTE J1650-500 may not produce the same scale of jets as their supermassive counterparts, they may offer a more intimate view of the processes that govern jet formation. XTE J1650-500 might serve as a model for understanding how jets are produced in less energetic environments. Given its relatively modest size, its jets might be less powerful but still exhibit the same underlying mechanisms. Studying the properties of these jets from smaller black holes could reveal new insights into the nature of magnetic fields around black holes, how matter is accelerated to relativistic speeds, and how energy is transferred from the black hole to the surrounding space. This could ultimately improve our understanding of how jets are produced in black holes of all sizes, not just the supermassive ones. The idea of black hole mergers is also a critical consideration in the study of systems like XTE J1650-500. While stellar mass black holes like XTE J1650-500 typically don't produce the kind of powerful gravitational waves that are emitted during the mergers of larger black holes, their behavior in binary systems can still offer important clues. When two black holes orbit one another in a binary system, their gravitational pull on each other leads to the emission of gravitational waves, which are ripples in spacetime. These waves carry information about the masses, spins, and other properties of the black holes involved in the merger. By studying the dynamics of binary systems like XTE J1650-500, astronomers can learn more about the potential for black hole mergers to occur on a smaller scale. Although gravitational wave observatories like LIGO and Virgo have been primarily focused on detecting the mergers of large black holes, the detection of smaller black hole mergers could open up a whole new field of study. XTE J1650-500, being in a binary system with a companion star, presents a fascinating opportunity to study how black holes in these systems might evolve over time. Would a system like XTE J1650-500 eventually evolve into a merger? What would that merger look like, and how would it affect the surrounding environment? These are the kinds of questions that continue to drive research into small black hole systems. The broader implications of XTE J1650-500 also touch on the study of galaxy formation and evolution. Supermassive black holes are believed to play a central role in the formation and growth of galaxies, influencing the distribution of stars and the overall structure of the galaxy. However, stellar mass black holes, such as XTE J1650-500, might also have a role to play in shaping the environments in which they exist. In the case of XTE J1650-500, its presence in a binary system with a companion star could be part of a larger galactic ecosystem, affecting the way matter is distributed in its region of space. Black holes like XTE J1650-500 could also help us better understand the dynamics of stellar evolution and the life cycle of stars. The black hole's mass is thought to be the result of the collapse of a massive star at the end of its life. Understanding how black holes like XTE J1650-500 form and evolve can provide clues about how stars live and die. Are there particular types of stars that are more likely to form smaller black holes? What role do the surrounding environments play in shaping the evolution of these objects? The answers to these questions could change the way we think about stellar birth and death. As we continue to refine our techniques for detecting and observing black holes, systems like XTE J1650-500 will become increasingly important for studying the interplay between stars, black holes, and galaxies. In the future, the discovery of more small black holes could reveal a hidden population of objects that were previously overlooked. These small black holes might be the key to understanding many of the unanswered questions in astrophysics, from the formation of black holes to the way matter behaves under extreme conditions. XTE J1650-500 is far more than just a small black hole. It is a window into understanding the nature of black holes and all their diversity. From its low mass to its role in a binary system, it challenges our assumptions about how black holes form, grow, and interact with their surroundings. By studying XTE J1650-500 in greater detail, we not only uncover the mysteries of one of the smallest known black holes but also gain valuable insights into the broader processes that govern the universe. Whether through its effects on the accretion disk, the production of relativistic jets, or its potential for gravitational wave emissions, XTE J1650-500 continues to push the boundaries of what we know about black holes. Its discovery is just the beginning of a new chapter in the study of the universe's most mysterious objects. The study of XTE J1650-500 presents a unique opportunity to gain insights into the mechanics of black hole behavior, especially as it relates to the accretion process. The accretion of matter by a black hole is one of the most fundamental processes in astrophysics, as it plays a key role in understanding the growth of black holes, the formation of jets, and the emission of X-rays. While much of the attention on accretion disks has been focused on larger black holes, studying smaller black holes like XTE J1650-500 offers a fresh perspective on how accretion operates in different regimes. In the case of XTE J1650-500, its relatively small size means that the matter surrounding it behaves differently compared to larger black holes. The accretion disk, composed of gas, dust, and other material, doesn't reach the temperatures and luminosities associated with larger systems. The lower mass of XTE J1650-500 means that its gravitational pull is weaker, resulting in a less intense accretion disk that doesn't generate the high-energy X-rays typically observed in the most massive black holes. This more subdued activity is an important aspect of the system that is often overlooked in discussions about black holes, but it provides crucial information about the underlying physics. One of the critical ways in which smaller black holes like XTE J1650-500 differ from their larger counterparts is in the behavior of their relativistic jets. These jets, composed of material ejected from the region surrounding the black hole, are one of the most spectacular phenomena associated with black holes. In the case of XTE J1650-500, the relatively low mass of the black hole doesn't seem to produce jets with the same intensity as those seen around supermassive black holes, but this doesn't mean that it lacks jets altogether. Instead, it may offer a more nuanced view of jet formation and propagation. The jets produced by XTE J1650-500 likely involve much smaller amounts of matter being ejected at extremely high speeds. These jets, although less powerful than those found in larger black holes, could still offer valuable clues about how jets are formed and how they interact with the surrounding environment. The study of these smaller jets could lead to a better understanding of the role of magnetic fields, the interaction between the accretion disk and the black hole's event horizon, and the process by which material is accelerated to relativistic speeds. Furthermore, the study of these smaller black holes also has important implications for our understanding of the cosmic environment. XTE J1650-500 resides in a binary system with a companion star, and this relationship is crucial for understanding how black holes accrete material and how they interact with nearby stars. The gravitational pull of the black hole can strip material from its companion star, forming an accretion disk and feeding the black hole. This process not only provides valuable information about the dynamics of binary systems, but also helps us understand how material behaves in extreme gravitational fields. The interactions between black holes and their companion stars can give rise to a wide variety of phenomena, including X-ray emissions, outflows, and other types of radiation that can be detected by astronomers. XTE J1650-500 is an example of how black hole systems can play a key role in the evolution of their surrounding environments. As the black hole continues to pull material from its companion star, it can influence the star's life cycle, affecting its future evolution and potentially leading to the formation of other exotic objects. The presence of a black hole in a binary system like XTE J1650-500 can even affect the chemical composition of the surrounding interstellar medium, contributing to the creation of new elements and influencing the formation of future generations of stars. The discovery of black holes like XTE J1650-500 also underscores the importance of studying binary systems in general. Binary star systems, where two stars orbit around a common center of mass, are incredibly common in the universe. These systems often serve as laboratories for studying extreme physics and astrophysical phenomena, as the interactions between the stars can lead to the formation of objects like white dwarfs, neutron stars, and black holes. By studying systems like XTE J1650-500, astronomers can gain a deeper understanding of the processes that govern binary evolution and the conditions under which black holes are formed. In addition to its role in binary systems, XTE J1650-500 also highlights the importance of stellar evolution and the processes that lead to the formation of black holes. The birth of a black hole typically involves the collapse of a massive star at the end of its life. The mass of the star determines the type of remnant it will leave behind after the collapse. For stars with masses several times that of the Sun, the collapse will result in the formation of a black hole. However, the exact mass threshold for black hole formation is still a subject of active research. XTE J1650-500, with its relatively small mass, raises important questions about the lower limits of black hole formation. Can a star with a mass below a certain threshold still form a black hole, or does it instead leave behind a neutron star or another type of remnant? The lower mass of XTE J1650-500 also has implications for the study of stellar populations. By studying black holes like XTE J1650-500, astronomers can learn more about the types of stars that are capable of producing such objects. This knowledge can help us better understand the diversity of stellar populations in the universe and the conditions required for the formation of black holes. The discovery of a small black hole in a binary system also sheds light on the role of these systems in the overall structure of galaxies. While supermassive black holes are thought to play a central role in the formation and growth of galaxies, stellar mass black holes like XTE J1650-500 could also play a significant role in the evolution of their host galaxies. The study of black holes like XTE J1650-500 also has far-reaching implications for our understanding of fundamental physics. Black holes, especially those in the stellar mass range, provide a unique laboratory for testing the laws of physics in extreme conditions. The strong gravitational fields around black holes, along with the high-energy environments, allow scientists to test theories of relativity, quantum mechanics, and particle physics. XTE J1650-500, as one of the smallest known black holes, presents an opportunity to study these extreme conditions in a relatively low-mass system, offering valuable insights into the fundamental nature of space and time. In particular, XTE J1650-500 offers a unique testing ground for theories of accretion, magnetic fields, and relativistic jets. While much of the focus in astrophysics has been on larger black holes, smaller black holes like XTE J1650-500 may reveal new aspects of these processes that have been hidden in larger systems. For example, the formation and behavior of relativistic jets in lower-mass black holes could offer a more detailed understanding of how matter is accelerated to relativistic speeds and how energy is transferred from the black hole to its surroundings. By studying these jets in smaller black holes, we can learn more about the fundamental mechanisms behind jet formation and their role in the larger-scale structure of galaxies. Moreover, XTE J1650-500 could provide important clues about the nature of dark matter and the behavior of material in extreme environments. Some theories suggest that dark matter, the mysterious substance that makes up much of the universe's mass, may interact with black holes in ways that are not yet understood. By studying the material around XTE J1650-500, astronomers may be able to uncover new clues about the nature of dark matter and its interactions with ordinary matter. This could have profound implications for our understanding of the universe as a whole, shedding light on one of the most elusive components of the cosmos. As we continue to explore black holes like XTE J1650-500, the boundaries of our understanding of the universe continue to expand. With the ongoing development of advanced telescopes, observatories, and computational tools, we are now able to peer deeper into the universe than ever before. XTE J1650-500 serves as a perfect example of how even the smallest black holes can reveal profound insights into the workings of the universe. From their role in binary systems to their influence on stellar evolution, black holes like XTE J1650-500 offer a unique perspective on the fundamental processes that govern the cosmos. Ultimately, the study of XTE J1650-500 is not just about understanding one particular black hole. It is about gaining insights into the nature of black holes as a class of objects, from the smallest to the largest. It is about unraveling the mysteries of accretion, jet formation, and the interaction of black holes with their environment. And it is about expanding our understanding of the universe itself, how it works, how it evolves, and how the most extreme objects in the universe shape the space around them. The fascination with XTE J1650-500 also ties into a broader interest in the formation and distribution of black holes across the universe. As astrophysicists continue to refine models of stellar evolution and black hole formation, this relatively small black hole offers a key piece of the puzzle. It challenges existing models by representing one of the smallest known stellar mass black holes, pushing the boundaries of what we thought was possible in terms of the mass range in which black holes can form. Despite the fact that XTE J1650-500 is relatively small, it shares many characteristics with its more massive counterparts. The binary system it inhabits offers a rich field of study for understanding how black holes interact with their companions. This system is particularly interesting because of the material transfer that occurs from the companion star to the black hole. The star's matter is pulled into the accretion disk, heated to extreme temperatures, and radiated in the form of X-rays. These high-energy X-rays are some of the primary ways that astronomers are able to detect and study black holes, as the radiation emitted from the hot gas in the accretion disk provides vital information about the black hole's behavior and its interaction with surrounding matter. Interestingly, XTE J1650-500's relatively small mass implies a different kind of accretion behavior compared to more massive black holes. The reduced mass means that the black hole's gravitational pull is weaker, and the surrounding accretion disk behaves differently. The dynamics of the accretion disk around XTE J1650-500 are subtle and offer astrophysicists the chance to study a different regime of accretion physics. Researchers can probe how material behaves in less intense gravitational fields, and how the energy output from the disk varies when the central black hole has a smaller mass. In a broader context, the discovery of smaller black holes like XTE J1650-500 is part of a growing effort to map the population of stellar mass black holes across the universe. Until recently, many black holes detected by astronomers were found in systems where the black holes were significantly more massive, such as those in high-mass X-ray binaries or the remnants of supernova explosions. However, XTE J1650-500's discovery challenges the idea that black holes need to be large to form, and provides a glimpse into the diversity of black holes in terms of mass and formation history. Understanding how these smaller black holes form and how they behave provides us with crucial data for building a more complete understanding of black hole populations. While the study of smaller black holes, like XTE J1650-500, may seem like a niche area of research, it has profound implications for our understanding of the universe as a whole. Black holes of all sizes play important roles in the evolution of galaxies, the formation of stars, and the dynamics of cosmic structures. They serve as laboratories for testing some of the most fundamental laws of physics, including general relativity, quantum mechanics, and the behavior of matter under extreme conditions. By studying these exotic objects, astronomers are not only expanding our understanding of astrophysics, but also providing important clues about the broader nature of the universe itself. One key area where XTE J1650-500 provides valuable insights is in the realm of gravitational waves. Gravitational waves, which were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, are ripples in spacetime caused by massive objects accelerating or colliding. The detection of gravitational waves from black hole mergers has opened up a new era in astrophysics, allowing us to observe phenomena that were previously undetectable by traditional telescopes. While XTE J1650-500 itself may not be directly involved in any significant gravitational wave events, its study helps astronomers refine models of black hole mergers and the conditions under which these events might occur. The behavior of smaller black holes, such as XTE J1650-500, can influence the interpretation of gravitational wave signals. By studying these black holes, we can improve our understanding of how different black hole masses and accretion processes affect the merger process. For example, understanding the mass distribution of black holes like XTE J1650-500 can help us predict the likelihood of mergers between smaller black holes and larger black holes, which could lead to the formation of intermediate mass black holes, an area of significant interest in gravitational wave research. In addition to gravitational wave science, the study of XTE J1650-500 helps inform the study of the cosmic X-ray background. The X-ray emission from XTE J1650-500's accretion disk adds to the broader picture of X-ray sources throughout the universe. Understanding the nature of these X-ray sources, especially from relatively small black holes, is essential for building a comprehensive understanding of the X-ray background. By analyzing the unique signatures of X-rays emitted by smaller black holes, astronomers can gain insights into the properties of other X-ray sources in the universe and the broader processes that govern high-energy radiation across the cosmos. Another fascinating aspect of XTE J1650-500 is its potential contribution to the study of the supernovae and stellar remnants. As XTE J1650-500 is a stellar mass black hole, it is the end result of the evolution of a massive star. When a massive star exhausts its nuclear fuel, it undergoes a dramatic collapse that leads to a supernova explosion, which can leave behind a variety of stellar remnants, including neutron stars and black holes. The exact process by which some stars form black holes rather than neutron stars is still not fully understood, but XTE J1650-500 provides a crucial clue. It likely formed from a star with a mass that was just high enough to collapse into a black hole but not massive enough to produce a more massive black hole. The formation of stellar mass black holes like XTE J1650-500 is a key area of ongoing research in stellar astrophysics. Scientists are still working to understand the precise conditions under which a star will form a black hole and the factors that influence its mass. By studying black holes such as XTE J1650-500, astronomers can learn more about the processes that govern stellar evolution and the thresholds that determine whether a star will become a black hole, a neutron star, or another type of remnant. XTE J1650-500's relatively low mass also makes it an excellent candidate for further study in the search for intermediate mass black holes. These black holes, which have masses between stellar mass black holes and supermassive black holes, are theorized to exist but have been difficult to detect. The discovery of XTE J1650-500 suggests that stellar mass black holes may be part of a continuous range of black hole masses, and the study of objects like this one could help bridge the gap between smaller stellar mass black holes and the supermassive black holes found at the centers of galaxies. While the study of XTE J1650-500 and similar black holes is still in its early stages, the potential for discovery is vast. These black holes provide us with a unique perspective on the behavior of matter under extreme gravitational forces, the nature of accretion processes, and the interplay between black holes and their surrounding environments. Every new piece of data we collect from systems like XTE J1650-500 brings us closer to a deeper understanding of the universe and the fundamental forces that govern it. As we continue to explore the significance of XTE J1650-500, it's important to remember that its discovery is not just about uncovering new details about one black hole in isolation. It's about fitting it into the broader context of black hole physics and the mysteries of the cosmos. With each discovery, such as that of XTE J1650-500, we begin to question the nature of the universe in new ways and revise the existing paradigms of astrophysics. One area where this black hole may contribute to our understanding is the study of black hole spin. The spin of a black hole is a critical feature that influences its accretion disk, the formation of relativistic jets, and the emission of X-rays. In many cases, the spin of a black hole is closely tied to the black hole's history, as its spin can change over time as it accretes material or merges with other objects. For black holes like XTE J1650-500, the spin rate could provide important clues about the history of its formation and its interaction with the companion star. Astronomers study black hole spin by examining the X-rays emitted from the accretion disk. These X-rays exhibit specific characteristics, such as broadening or shifting in energy, that can be used to infer the black hole's spin. The accretion disk surrounding XTE J1650-500 is likely spinning at a high rate, and this provides an opportunity for astronomers to measure the black hole's spin with great precision. By doing so, they could reveal more about how black holes grow and evolve over time, and how the spin rate of a black hole affects its behavior. The small size of XTE J1650-500 also means that its spin is particularly intriguing. Smaller black holes tend to spin faster than their more massive counterparts due to the conservation of angular momentum. As a black hole accretes material, the mass and angular momentum of the material is added to the black hole, causing it to spin faster. However, in smaller black holes like XTE J1650-500, the spin rate can approach the theoretical limit of the fastest spin possible for a black hole. Studying the spin of this black hole can give astronomers a better understanding of the physics behind this phenomenon, and whether the theoretical limits of black hole spin are reached in these systems. Beyond its scientific implications, XTE J1650-500 also offers a deeper philosophical reflection on the nature of black holes and the unknown regions of space. The very existence of objects like XTE J1650-500, which seem to defy the conventional boundaries of what is possible for stellar mass black holes, forces us to reconsider the nature of the universe itself. How much do we truly understand about the cosmos, and how much of it remains a mystery, waiting to be uncovered? One of the most intriguing aspects of black holes in general is their role as cosmic laboratories for testing the limits of physics. At the event horizon of a black hole, the laws of physics as we know them break down, and general relativity and quantum mechanics come into conflict. This intersection of the two pillars of modern physics provides a unique opportunity to test theories and refine our understanding of the fundamental forces that govern the universe. By studying black holes like XTE J1650-500, which challenge our current understanding of black hole mass ranges, we may be able to unlock the mysteries that lie at the heart of the universe. The small size of XTE J1650-500 also raises new questions about the relationship between black holes and the surrounding environment. In the case of larger black holes, the powerful gravitational forces and the resulting radiation have significant effects on the galaxies in which they reside. Supermassive black holes, in particular, can influence the formation of stars, the motion of galaxies, and the overall structure of the cosmos. However, the influence of smaller black holes like XTE J1650-500 is less well understood. While their gravitational effects are weaker, they still have a significant role to play in the dynamics of their immediate surroundings. Studying these smaller black holes can help us understand the role that black holes of all sizes play in the evolution of galaxies and the cosmic structure. Moreover, XTE J1650-500 is a part of a growing catalog of black holes, some of which are in binary systems like this one. As the number of detected black holes increases, so too does our ability to make statistical comparisons. With a larger sample size, astronomers can better understand the variety of black hole masses, spins, and behaviors that exist in the universe. Systems like XTE J1650-500 provide crucial data points that allow scientists to refine their models of black hole formation, evolution, and interaction with their environment. The role of smaller black holes in stellar evolution is also of particular interest. XTE J1650-500, with its mass that places it on the lighter end of the stellar mass black hole spectrum, presents a unique case. It may have formed from a star that wasn't massive enough to collapse into a larger black hole, but was still able to create a black hole in its final stages. This raises important questions about the mass thresholds for black hole formation and the physical processes that govern this transition. Understanding these processes could provide new insights into how black holes form in different types of stars and how they impact the evolution of their host galaxies. As we continue to explore XTE J1650-500, it is important to consider the broader context of black hole research and the challenges that still lie ahead. While we have made great strides in understanding these mysterious objects, much remains unknown. For example, the precise mechanisms that govern black hole formation, the conditions required for a stellar remnant to collapse into a black hole, and the nature of black hole mergers are all still active areas of research. XTE J1650-500 represents just one small piece of the puzzle, and as we gather more data, we will be able to refine our models and improve our understanding of these cosmic giants. In the future, The study of black holes like XTE J1650-500 could also contribute to our understanding of the intergalactic medium and the role that black holes play in the distribution of matter across the universe. The energy released from the accretion disk, the jets of matter ejected from black holes, and the radiation emitted by these objects can all influence the surrounding gas and stars. By studying the feedback mechanisms between black holes and their environments, we can gain deeper insights into the processes that govern the growth and evolution of galaxies and the larger structure of the universe. Another exciting avenue of research lies in the potential discovery of intermediate mass black holes, IMBHs, which could help bridge the gap between stellar mass black holes like XTE J1650-500 and the supermassive black holes found in the centers of galaxies. The discovery of IMBHs would revolutionize our understanding of black hole formation and evolution, shedding light on how supermassive black holes may have formed in the early universe. While no confirmed IMBH has been found, black holes like XTE J1650-500 may hold clues to the elusive nature of these objects. Understanding the growth of black holes across different mass ranges could help astronomers pinpoint the mechanisms behind supermassive black hole formation. XTE J1650-500 is not only a remarkable object in its own right, but also serves as a window into the deeper mysteries of black hole physics. It challenges our understanding of black hole mass ranges, provides new insights into accretion disk behavior, and offers a valuable context for studying the formation and evolution of black holes. While this small black hole may seem like a modest subject of study, it holds profound implications for our understanding of the universe. As we continue to unravel the mysteries surrounding XTE J1650-500, we are reminded of the fundamental nature of scientific exploration: to question, to probe, and to discover. Black holes like XTE J1650-500 reveal the complexity and beauty of the universe in ways that go beyond what we can see. They invite us to look deeper, to challenge our assumptions, and to embrace the unknown as a source of wonder and inspiration. Through the study of black holes, we not only learn more about the cosmos but also come to understand the limits of our knowledge and the boundless possibilities that lie ahead. As we continue our deep dive into the enigmatic nature of XTE J1650-500, we can explore further the significance of its discovery in the wider context of astrophysical research and its potential impact on our understanding of the universe. One of the most intriguing aspects of XTE J1650-500 is how it fits into the broader landscape of stellar mass black holes, which are typically found in binary systems, as in the case of XTE J1650-500. These systems are incredibly important for understanding the processes that lead to black hole formation and the factors that govern their behavior. In the case of XTE J1650-500, the black hole is in a binary system with a companion star, and this is an essential part of what makes it so significant. The material from the companion star is funneled onto the black hole via an accretion disk, which not only causes the black hole to grow but also leads to the emission of X-rays. This process is particularly useful in black hole studies because the X-ray emissions can reveal a wealth of information about the black hole's mass, spin, and the behavior of the accretion disk. This allows scientists to make more precise measurements of the properties of black holes like XTE J1650-500. XTE J1650-500 is particularly fascinating because it challenges some of our expectations about how stellar mass black holes behave. While many of the well-known black holes are more massive, the discovery of such a relatively small black hole forces scientists to reconsider their models of black hole formation. In particular, it raises important questions about the processes that occur during the death of stars and how these processes lead to the formation of a black hole. Could XTE J1650-500 represent a new class of stellar mass black holes that were previously undetected due to their small size? What does its discovery tell us about the possible diversity of black holes that may exist in the universe? This small black hole could also provide significant insights into the physics of matter under extreme conditions. The environment near a black hole, particularly the accretion disk, is one of the most hostile and extreme environments in the universe. The temperature in the accretion disk of XTE J1650-500, for example, can reach millions of degrees, causing the gas to emit high-energy X-rays and gamma rays. Studying this energy allows scientists to probe the behavior of matter in these extreme conditions and test theories of physics in regimes that cannot be replicated in laboratories on Earth. XTE J1650-500 also exemplifies one of the challenges in modern astrophysics: detecting and studying black holes that are not easily observable. Many black holes are surrounded by dense clouds of gas and dust that obscure our view of them, making it difficult to observe them directly. However, by studying the X-rays emitted from the accretion disk, astronomers can detect the presence of black holes even if they are hidden behind clouds of gas. This is one of the key reasons why XTE J1650-500 is so important. It was detected through its X-ray emissions, which allowed scientists to infer its mass and other properties. Without this method of detection, smaller black holes like XTE J1650-500 might have remained hidden from view. The importance of XTE J1650-500 also extends to its potential to help resolve some of the most fundamental questions in astrophysics. One of the biggest questions that remain unanswered is the nature of the event horizon of a black hole, the boundary beyond which not even light can escape. While the event horizon is an essential concept in the theory of general relativity, it is still not entirely clear how it behaves in practice. The small size of XTE J1650-500 makes it a particularly interesting target for studying the event horizon, as the smaller the black hole, the more pronounced the effects of the event horizon are likely to be. By carefully studying the emissions from the accretion disk and the behavior of the material near the event horizon, scientists can test our theories of general relativity and better understand the true nature of black holes. One of the exciting prospects of studying small black holes like XTE J1650-500 is that they may provide insights into the broader structure of the universe. Black holes, especially stellar mass ones, are thought to be a fundamental part of galaxy formation and evolution. The material that falls into a black hole can influence the surrounding gas and stars, which in turn affects the larger structure of the galaxy. Understanding the behavior of black holes in binary systems, like XTE J1650-500, can help astronomers piece together how black holes influence the galaxies in which they reside. This is crucial for understanding the life cycle of galaxies and how galaxies, stars, and black holes interact with each other. Additionally, as we continue to probe the properties of XTE J1650-500, we could gain insights into the elusive nature of dark matter. Dark matter is one of the greatest mysteries in modern astrophysics. It does not emit or interact with electromagnetic radiation, which makes it invisible to our current methods of observation. However, its presence is inferred by its gravitational effects on visible matter. It has been suggested that small black holes, like XTE J1650-500, could potentially help us understand the role of dark matter in the universe. If these black holes are found to be interacting with dark matter in some way, it could provide a valuable clue in the search for dark matter and help solve one of the most significant mysteries in physics. The study of XTE J1650-500 is also important for the field of gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as black holes. The detection of gravitational waves, first accomplished by LIGO in 2015, has opened up a new era of astrophysical research. While the study of gravitational waves from larger black hole mergers has been well established, smaller black holes like XTE J1650-500 may also produce detectable gravitational waves. As gravitational wave detectors improve, we may be able to use these waves to study black holes in even greater detail and refine our models of black hole formation and behavior. The potential detection of gravitational waves from XTE J1650-500 could provide further evidence of the fundamental role that black holes play in the structure and evolution of the universe. In a larger sense, the discovery and study of XTE J1650-500 reinforced the idea that the universe is full of surprises. For decades, astronomers have been searching for black holes, and while they have made incredible progress in understanding these objects, each new discovery, like XTE J1650-500, reveals that there is still so much we do not know. The universe is vast, complex, and full of mysteries, and XTE J1650-500 is a small piece of that grand puzzle. It serves as a reminder that there is always more to discover, and that our understanding of the cosmos is constantly evolving. Looking ahead, the future of black hole research is bright, and XTE J1650-500 may be just the tip of the iceberg. As technology improves, new methods of detecting and studying black holes will likely be developed, allowing us to explore even the most distant and elusive objects in the universe. The study of XTE J1650-500 has already provided valuable insights into the nature of black holes, and as we continue to learn from it, we can expect to unlock even more secrets about these fascinating and mysterious objects. XTE J1650-500 is not just a curiosity, it is a pivotal discovery that opens new doors for astrophysical research. Its small size, unique properties, and the insights it offers into the behavior of black holes challenge our current understanding of the cosmos. Through continued study, we can refine our models of black hole formation, accretion, and evolution, and push the boundaries of knowledge even further. As we continue to look to the stars, the discovery of black holes like XTE J1650-500 reminds us of the vastness of the universe and the boundless possibilities that lie ahead in our quest for understanding. XTE J1650-500 holds a unique place in the pantheon of black hole discoveries, serving as a testament to the extraordinary nature of the universe we inhabit. While it is still in its early stages of study, the data collected thus far has opened up numerous possibilities for the future of astrophysics. It challenges long-held assumptions and invites scientists to reconsider models that previously seemed well established. As we continue to peer deeper into the universe, black holes like XTE J1650-500 will undoubtedly guide our path, helping to shape our understanding of some of the most fundamental aspects of space and time. In many ways, the study of XTE J1650-500 is just the beginning. As the techniques for observing and understanding black holes continue to evolve, we may find that there are far more small black holes scattered across the galaxy, many of which could be hiding in plain sight. The technology of the future will allow us to detect these elusive objects with greater precision, expanding our knowledge of black holes and their role in the universe. With the discovery of XTE J1650-500, we now have another fascinating piece to add to the cosmic puzzle. By examining its mass, spin, and the dynamics of the system, we will continue to refine our understanding of black holes. Furthermore, this small black hole offers new insights into the formation of black holes in general. It raises the possibility that there are many other small, undetected black holes that could reveal a different story about stellar evolution than the one we've been telling for decades. As we explore these possibilities, we may discover that black holes come in a broader range of sizes and properties than previously thought, opening up a new chapter in our understanding of the universe. Beyond just the technical details of black holes, the discovery of XTE J1650-500 is also a humbling reminder of the vastness and mystery of the cosmos. While we have made incredible strides in our understanding of the universe, every discovery like this one highlights just how much there is still left to learn. Each step forward brings us closer to answering some of the most profound questions in science. What are black holes made of? How do they form? What lies inside the event horizon? And perhaps most tantalizing of all, can anything escape a black hole? The study of XTE J1650-500, and black holes in general, will continue to challenge our most fundamental theories about the nature of reality itself. As we look to the future, there is much to be excited about in the realm of black hole research. New telescopes, better computational models, and more sensitive instruments will provide even more detailed data, allowing us to explore the true nature of black holes and the environments around them. The next few decades could bring an explosion of discoveries that further our understanding of not only XTE J1650-500 but the entire category of stellar mass black holes. The knowledge gained from these observations will not only shed light on black holes themselves but could also unlock deeper mysteries about the universe, such as the nature of dark matter, dark energy, and the fundamental laws of physics. In addition, the study of smaller black holes like XTE J1650-500 may yield clues about the early universe. Black holes are thought to play a critical role in the evolution of galaxies, and their formation mechanisms may be tied to the very origins of cosmic structure. By better understanding how small black holes form and evolve, we could gain insights into the processes that occurred shortly after the Big Bang. These discoveries could be instrumental in helping scientists answer some of the biggest questions about the universe's origins, such as the nature of the cosmic inflationary period, the formation of the first stars, and the processes that led to the creation of galaxies, stars, and planets. There is also a deep philosophical element to the study of black holes that makes them fascinating not just to scientists but to anyone with a curiosity about the nature of existence. Black holes challenge our conceptions of time and space, as they warp space-time so dramatically that they create a region of no return, an event horizon, where the laws of physics as we know them begin to break down. This extreme warping of space-time forces us to rethink the very nature of gravity, causality, and even the passage of time itself. As we learn more about black holes like XTE J1650-500, we are forced to confront fundamental questions about the nature of the universe and our place within it. Moreover, the study of XTE J1650-500 represents a significant milestone in the development of black hole science, particularly in the context of detecting smaller black holes. For years, most of the attention has been focused on supermassive black holes, which reside at the centers of galaxies and can have masses billions of times that of the Sun. However, smaller black holes, like those in binary systems such as XTE J1650-500, offer unique insights into the processes of star death and black hole formation. They serve as a crucial link between stellar evolution and the more massive black holes that are often the focus of astrophysical research. XTE J1650-500 also highlights the importance of multi-wavelength astronomy. The discovery of this black hole was made possible by observations in the X-ray spectrum, demonstrating once again the value of looking at the universe in different wavelengths. The light we observe with our eyes, visible light, is just a small fraction of the entire electromagnetic spectrum. To truly understand the universe, we must study it across the entire range of wavelengths, from radio waves to gamma rays. XTE J1650-500's discovery and subsequent study reinforce this approach and remind us that much of the most important information about the universe lies beyond the visible spectrum. As we continue to explore the universe and uncover more about objects like XTE J1650-500, we will undoubtedly face challenges and obstacles. But these challenges are what make the journey so rewarding. Each new discovery leads to more questions, and each question brings us closer to understanding the fundamental workings of the cosmos. XTE J1650-500 may be small in terms of its mass compared to other known black holes, but its implications are anything but small. This black hole represents a piece of a much larger puzzle, one that will take years, if not centuries, to fully solve. As future generations of astronomers, physicists, and space enthusiasts look back at the discovery of XTE J1650-500, they will undoubtedly recognize it as one of the milestones in our quest to understand the most mysterious and elusive objects in the universe. It may be small, but its significance is immense. By continuing to study black holes like XTE J1650-500, we are not just learning about these strange objects, we are learning about the very fabric of the universe itself. As we continue to study black holes like XTE J1650-500, the discoveries will undoubtedly help us refine existing theories and potentially introduce entirely new paradigms of understanding. The mysteries surrounding black holes push the boundaries of what we know about physics, from quantum mechanics to general relativity, and even the nature of gravity itself. XTE J1650-500, with its peculiar characteristics and relatively small mass, may hold clues to some of these unsolved questions. Its study forces us to reconsider the nature of stellar remnants, the process by which stars collapse into black holes, and the ways in which these cosmic entities affect the surrounding environment. One of the most intriguing aspects of XTE J1650-500 is its potential to provide insight into the process of stellar collapse. Black holes form when massive stars undergo supernova explosions, causing their cores to collapse under their own gravitational force. However, the precise conditions that determine whether a star will form a black hole or leave behind a neutron star, another form of stellar remnant, remain an area of active research. XTE J1650-500, being smaller than other black holes detected in similar systems, offers a unique opportunity to study this process in more detail. If smaller black holes like XTE J1650-500 are more common than previously thought, it could suggest that the mechanism behind black hole formation is more complex than we once believed, and that a wider variety of stellar types could lead to the formation of black holes. Additionally, XTE J1650-500's small size opens the door to the exploration of stellar mass black holes, those that have masses in the range of a few to several times that of the Sun. Historically, these black holes have been somewhat elusive, as they tend to be found in binary systems, making them difficult to detect. The presence of a companion star that emits radiation when it is pulled towards the black hole provides the necessary clues to detect these hidden objects. XTE J1650-500's discovery showcases the technological advances in observational instruments, which have allowed scientists to detect such small black holes with greater accuracy. These instruments, such as the Rossi X-ray Timing Explorer, RXT, provide crucial data on the behavior of matter in the vicinity of black holes, which can help scientists understand the interaction between black holes and their surroundings, as well as the physics of matter under extreme conditions. The discovery of XTE J1650-500 also emphasizes the importance of precision measurements and the need for continued advancements in astrophysical instrumentation. Observing a black hole of this size, and accurately determining its properties, is a feat that requires cutting-edge technology. The ability to measure X-rays with such high precision allows astronomers to detect the subtle signals from matter being heated to incredibly high temperatures as it spirals into the black hole. This information is invaluable, as it provides insight into the accretion process, the way in which black holes feed on surrounding matter, and the way in which these processes shape the environments around them. One area where XTE J1650-500 is expected to have a significant impact is in the study of black hole spin. The spin of a black hole, which refers to its rotational speed, plays a critical role in the behavior of the surrounding accretion disk and can influence the way in which matter is drawn into the black hole. The spin of a black hole is closely related to the angular momentum it has accumulated from the material it has consumed. Studying the spin of smaller black holes like XTE J1650-500 can provide new insights into the mechanisms of black hole formation and growth, as well as the ways in which black holes interact with their environment. By measuring the spin of XTE J1650-500, scientists may be able to place more constraints on the models of black hole evolution, shedding light on how black holes of various sizes acquire their mass and spin over time. Another fascinating aspect of studying black holes like XTE J1650-500 is the potential for discovering new physics beyond the standard model. Black holes are among the most extreme environments in the universe, where the laws of physics as we understand them break down. For example, near a black hole's event horizon, gravity becomes so intense that it warps spacetime itself, creating an environment where classical physics no longer applies. This makes black holes an ideal place to test our theories of gravity and quantum mechanics, potentially revealing new phenomena that cannot be explained by current models. The discovery of smaller black holes, such as XTE J1650-500, may provide the perfect laboratory for studying quantum effects in strong gravitational fields and may even offer clues to the unification of general relativity and quantum mechanics. The relationship between black holes and their host galaxies is another area where XTE J1650-500 could offer valuable insights. It is widely accepted that black holes, particularly supermassive black holes, play a crucial role in the formation and evolution of galaxies. However, the role of stellar mass black holes, such as XTE J1650-500, is less well understood. These smaller black holes may not only be important for the dynamics of individual star systems, but could also influence the larger galactic environment. For example, black holes may act as a mechanism for regulating star formation by heating up or expelling gas from their surroundings. Understanding the role of smaller black holes in galactic evolution could help scientists better understand the processes that shape the structure of the universe. XTE J1650-500's discovery is also a reminder of how little we still know about the most fundamental aspects of the cosmos. Black holes challenge our understanding of matter, energy, and the very fabric of space-time. While scientists have made tremendous strides in the study of these enigmatic objects, there is still much to learn. Each new black hole discovered adds a new piece to the puzzle and provides fresh insights into the nature of the universe. The more we study black holes like XTE J1650-500, the more we are forced to confront the limitations of our current theories and the vastness of the unknown. Ultimately, the significance of XTE J1650-500 extends far beyond its status as a small black hole. It serves as a focal point for a wide range of scientific inquiries, from the nature of black hole formation to the behavior of matter under extreme conditions. It challenges our current models of stellar evolution, forces us to reconsider our understanding of gravity and spacetime, and invites us to look more deeply at the role of black holes in shaping the universe. As we continue to gather data and refine our techniques for studying these mysterious objects, the future of black hole research looks incredibly promising. XTE J1650-500 may be just one small black hole in the vast expanse of space, but it represents a giant leap forward in our understanding of the universe. With every new discovery, we come closer to unlocking the secrets of the cosmos and unraveling the mysteries that have long eluded us. Whether through the study of XTE J1650-500 or other stellar mass black holes, we are poised to make groundbreaking advancements in the years to come, further solidifying our place in the ever-evolving journey of cosmic exploration. The implications of XTE J1650-500's discovery extend beyond the field of black hole research. The study of such objects is intrinsically tied to the broader goals of astrophysics, understanding the fundamental processes of the universe, investigating the forces that shape cosmic evolution, and probing the mysteries of spacetime itself. By exploring stellar mass black holes like XTE J1650-500, scientists are pushing the boundaries of both observational technology and theoretical physics, challenging our understanding of the cosmos in profound ways. One of the most intriguing aspects of studying objects like XTE J1650-500 is the opportunity they present to test our understanding of the extreme environments that exist near black holes. The region surrounding a black hole, known as the accretion disk, is one of the most dynamic and energetic areas in the universe. As matter falls toward a black hole, it is heated to temperatures that are millions of degrees, causing it to emit powerful radiation in the form of X-rays and other high-energy signals. Observing these emissions provides valuable insights into the nature of the material surrounding the black hole and the processes that govern its behavior. For years, astronomers have been using X-ray telescopes to study the radiation emitted by matter as it is drawn into black holes. However, the challenge lies in detecting and analyzing the faint signals produced by smaller black holes like XTE J1650-500. These objects are often buried in the noise of the universe, making them difficult to detect with traditional methods. It was only with the advent of more advanced technologies and the development of sensitive X-ray detectors that astronomers were able to pinpoint the location of XTE J1650-500. This discovery has not only provided valuable data on the black hole itself but has also opened up new avenues for studying other faint or hidden black holes that may be lurking in our galaxy. The study of black holes, particularly stellar mass black holes like XTE J1650-500, is also crucial for understanding the life cycle of stars. Stellar mass black holes are the remnants of massive stars that have reached the end of their lives and undergone a supernova explosion. The properties of these black holes, such as their mass, spin, and accretion rates, are deeply influenced by the characteristics of the progenitor star. By studying black holes like XTE J1650-500, scientists can learn more about the processes that lead to the formation of black holes and the various stages of stellar evolution that precede them. Furthermore, the discovery of smaller black holes like XTE J1650-500 challenges our traditional notions about the formation and distribution of black holes in the universe. It was once believed that black holes, particularly stellar mass black holes, would only form from very massive stars, with masses well beyond the typical range of ordinary stars. However, the existence of XTE J1650-500 suggests that smaller black holes may be more common than previously thought. This finding could have important implications for our understanding of the demographics of black holes in the universe, and may even shed light on the mechanisms behind the formation of supermassive black holes, which reside at the centers of most galaxies. As we continue to study black holes like XTE J1650-500, we are also gaining insight into the behavior of matter in extreme environments. The accretion disk around a black hole is one of the most interesting phenomena in astrophysics, as it provides a natural laboratory for studying the interaction between matter and gravity. When matter falls into a black hole, it is subjected to incredibly intense gravitational forces, which cause it to undergo a variety of complex physical processes. For example, the material in the accretion disk experiences a process known as angular momentum transfer, where the rotational motion of the material is transferred to the black hole itself. This process can lead to the emission of high-energy radiation, including X-rays and gamma rays, which can provide valuable information about the inner workings of the black hole. Moreover, the intense gravitational forces near a black hole create a phenomenon known as gravitational lensing, where the light from objects behind the black hole is bent and distorted as it passes near the black hole's event horizon. This effect, which is a direct consequence of Einstein's theory of general relativity, has been observed in several black hole systems and provides further evidence of the warping of spacetime caused by the immense gravitational pull of black holes. Studying gravitational lensing in systems like XTE J1650-500 can help astronomers better understand the nature of spacetime and the behavior of light in the presence of such extreme gravitational fields. The importance of XTE J1650-500 in the context of astrophysics goes beyond just its physical characteristics. It also serves as a reminder of how much we still have to learn about the universe. Even with all the advancements in technology and the wealth of data that has been gathered, black holes remain one of the most enigmatic and mysterious objects in the cosmos. They represent the limits of our understanding of physics, and each new discovery, like that of XTE J1650-500, brings us closer to unlocking their secrets. In the future, we can expect further breakthroughs in black hole research, driven by technological advancements in both observational instruments and computational models. New telescopes, such as the upcoming James Webb Space Telescope and the planned Event Horizon Telescope, will allow astronomers to observe black holes in unprecedented detail. These instruments will be able to study the behavior of matter as it falls into black holes, measure the spin and mass of these objects with greater precision, and explore the role of black holes in the formation and evolution of galaxies. As our understanding of black holes continues to evolve, it is likely that XTE J1650-500 and similar objects will play a key role in shaping our knowledge of the universe. Furthermore, the study of black holes like XTE J1650-500 is not only important for astrophysics, but also for the broader field of fundamental physics. Black holes are natural laboratories for testing our theories of gravity and quantum mechanics, and their extreme environments allow us to probe the nature of spacetime itself. For example, the study of the event horizon, the boundary beyond which nothing can escape the gravitational pull of a black hole, may eventually lead to a deeper understanding of quantum gravity, a field that seeks to reconcile the principles of general relativity with the laws of quantum mechanics. XTE J1650-500, with its relatively small size, provides an ideal case study for exploring these fundamental questions and may offer new insights into the nature of gravity at the most extreme scales. As we continue to study XTE J1650-500 and similar objects, we will likely encounter even more questions and mysteries, pushing the boundaries of what we know about the universe. Each discovery is a stepping stone toward a greater understanding of the cosmos, and the answers we find may open up entirely new avenues of research and exploration. The quest to understand black holes is one of the most exciting and rewarding endeavors in modern science, and the discovery of XTE J1650-500 represents just one chapter in this ongoing story. In the years to come, we may uncover even more surprises about black holes, both large and small, and learn how they influence the structure and evolution of galaxies. Whether through the study of their spin, their accretion disks, or the mysterious phenomena that occur near their event horizons, black holes will continue to be a central focus of astronomical research. XTE J1650-500 is just one example of the many exciting discoveries yet to come, and as we push the boundaries of our knowledge, the universe will continue to reveal its secrets, one black hole at a time. The discovery of XTE J1650-500 has also sparked a renewed interest in exploring the transitional region between neutron stars and black holes. Traditionally, the division between these two classes of stellar remnants was based on mass. Objects below a certain threshold collapse into neutron stars, while those above it collapse into black holes. However, XTE J1650-500, with its remarkably low mass, blurs that boundary and forces us to question just how clear-cut that division truly is. Neutron stars, which are essentially giant atomic nuclei held together by gravity, are themselves exotic objects. They exhibit phenomena such as pulsar emissions, intense magnetic fields, and even theoretical states of matter like quark-gluon plasma at their cores. The existence of an object like XTE J1650-500, which hovers near the mass limit between a neutron star and a black hole, opens the door to the possibility that more hybrid or intermediate objects may exist. These might include so-called quark stars, or other hypothesized exotic matter states that challenge our understanding of the equation of state, the relationship between pressure, temperature, and density, under extreme conditions. Another area where XTE J1650-500 proves to be an invaluable research asset is in the study of relativistic jets. Black holes, despite their reputation for consuming everything in their vicinity, are also capable of launching powerful jets of plasma that travel at near light speeds. These jets are produced by the interaction between the magnetic fields of the accretion disk and the rotational energy of the black hole itself, a mechanism often described by the Blandford-Znajec process. In the case of XTE J1650-500, observations have shown signs of relativistic jet activity, which is fascinating because it suggests that even small black holes can generate such enormous energy outputs under the right conditions. These jets can extend thousands of light-years into space and are responsible for shaping the interstellar medium, distributing elements, and possibly even influencing star formation in surrounding areas. The energy and structure of these jets give us insights into the role that black holes play in galactic ecology. More than just isolated cosmic anomalies, black holes act as engines that regulate and redistribute energy throughout the universe. That a black hole as small as XTE J1650-500 could still participate in this grand cosmic interplay is a humbling reminder that even the smallest components of the cosmos can wield extraordinary power. The detailed spectral studies of XTE J1650-500 have also yielded groundbreaking insights into the dynamics of inner accretion disks. Using high-resolution X-ray spectroscopy, astronomers have been able to observe iron K-alpha lines, specific X-ray emissions from iron atoms near the black hole. These lines get distorted by gravitational redshift and Doppler effects due to the immense velocities of orbiting matter and the intense gravity near the event horizon. The specific shape and breadth of these lines have been crucial for estimating the spin of XTE J1650-500. It turns out that this black hole is spinning rapidly, which provides further evidence that it must have either formed with this high angular momentum or been spun up by accreting matter over time. Spin, alongside mass, is one of the fundamental properties of a black hole. A high spin rate can significantly alter the geometry of space-time around the black hole, leading to phenomena such as frame dragging, where the black hole's rotation literally pulls spacetime along with it. This has major implications for time dilation, orbital stability of nearby matter, and the efficiency of energy extraction from the accretion disk. XTE J1650-500 thus serves not only as a rare case of a small-mass black hole, but also as a prime example of how spin affects black hole physics. There's also a fascinating theoretical debate around the possible echoes from past mergers or near-merger events. Some astrophysicists have suggested that XTE J1650-500 may not be a simple product of stellar collapse but could have formed through more exotic means, such as the collision of compact objects in a dense stellar environment. While there is currently no direct evidence of such a history in this case, the idea is tantalizing, especially in light of recent gravitational wave observations that have shown us that such mergers are not only real but more common than we once imagined. Gravitational wave astronomy has opened up an entirely new dimension of observing the universe, one that is not limited by light. Traditional telescopes observe electromagnetic radiation, but gravitational waves allow us to hear the ripples in spacetime caused by massive accelerating objects, like merging black holes. Although XTE J1650-500 has not yet been detected via gravitational waves, its small mass and dynamic characteristics make it a potential candidate for future detections, especially if it were ever to undergo a dramatic event such as a collision or sudden burst of accretion activity. Future detectors with enhanced sensitivity could one day pick up such signals, giving us real-time, multi-messenger data about what's happening in and around this elusive black hole. In considering the broader philosophical implications of XTE J1650-500, one can't help but reflect on how it illustrates the universe's capacity for contradiction and surprise. This tiny black hole, likely formed from a massive, dying star, encapsulates the paradoxes of cosmic evolution. It's both a remnant and a beginning, a relic of a once shining star and a newborn singularity altering space and time. It exists at the cusp of several scientific frontiers: mass, spin, formation, and high-energy phenomena, and challenges our models at every step. The mystery deepens when we remember that we have never directly seen a black hole. Everything we know about them comes from indirect evidence: X-ray emissions, gravitational effects on nearby objects, spectral analysis, and now gravitational waves. XTE J1650-500, then, is more than just a celestial object. It's a testament to the power of human inference and imagination. That we can deduce the presence, size, and even spin of something that does not emit light, from millions of light years away, speaks volumes about the ingenuity of observational astronomy and theoretical physics. As our tools become more sophisticated, and as we collect more data from long-term monitoring of black hole systems like XTE J1650-500, we're likely to uncover even more nuances. Instruments like NICER, NuSTAR, and Athena will give us the spectral and timing resolution needed to dissect these X-ray binaries with unprecedented clarity. With coordinated campaigns between ground and space-based observatories, we will soon be able to track how such black holes behave on minute-by-minute scales, watch accretion flares in real time, and maybe even predict their behavior based on disk instability models. This continued observation could help resolve long-standing debates about how accretion states evolve in stellar mass black holes, how jets are launched and quenched, and how material behaves in the innermost stable circular orbit, the closest distance a particle can orbit a black hole without falling in. For XTE J1650-500, a better understanding of these dynamics could validate or challenge some of the foundational models of high-energy astrophysics, such as the advection-dominated accretion flow (ADF) model, the Shakur-Sunyaev disk model, and general relativistic magnetohydrodynamic simulations. The fact that a black hole of this small scale can open up such vast domains of inquiry is a powerful reminder of the interconnectedness of cosmic phenomena. From the death of a single star comes not only a gravitational singularity, but also a cascade of energy, a burst of information, and a point of curiosity that spans disciplines from nuclear physics to quantum gravity. XTE J1650-500 may be small in mass, but it looms large in significance. It's worth contemplating how the smallest known black hole, XTE J1650-500, compels us to question not only the limits of our observational capabilities but also the very assumptions we hold about the nature of collapse, density, and even time. Its existence tugs at the lower edge of black hole formation, challenging the classic Chandrasekhar and Tolman, Oppenheimer, Volkoff limits that dictate the thresholds for white dwarfs and neutron stars, respectively. Historically, it was believed that once a stellar core surpasses around 3 solar masses, neutron degeneracy pressure would be insufficient to prevent further collapse into a black hole. But with XTE J1650-500 hovering at or just above that boundary, its mass estimated around 3.8 solar masses, possibly lower if revised again, we are forced to reconsider whether this boundary is fixed or more fluid than previously thought. Furthermore, the discovery and ongoing observation of XTE J1650-500 offer a window into the nature of the event horizon itself. The event horizon, that infamous point of no return, is the defining feature of any black hole. For smaller black holes, like this one, the event horizon is proportionally closer to the singularity, making relativistic effects like time dilation and gravitational redshift more extreme for matter near the boundary. In XTE J1650-500, matter in the accretion disk whirls around the black hole at relativistic speeds, and some of it gets heated to temperatures of millions of degrees Kelvin, radiating in X-rays. The shape and behavior of these X-ray signatures, how they rise, fall, and flicker, are telling astronomers about how space and time are twisted in that violent environment. More importantly, XTE J1650-500 provides a natural laboratory to test theories of quantum gravity. Since general relativity breaks down at the singularity and quantum mechanics has yet to be successfully merged with it, physicists are eager to examine black holes in every possible configuration. Small black holes are especially valuable in this respect because they might accentuate any quantum effects that larger black holes smooth out or mask. For example, theoretical proposals like Hawking radiation, the firewall paradox, and the holographic principle all posit that extreme gravitational systems like XTE J1650-500 could hold clues to reconciling gravity with quantum mechanics. Hawking radiation, in particular, is a fascinating concept in this context. Although it's currently undetectable with existing instruments, Hawking radiation is predicted to be inversely proportional to the mass of the black hole. That means smaller black holes like XTE J1650-500 should, in theory, radiate more intensely, though still incredibly weakly in practical terms. If any detectable signature of Hawking radiation were to emerge, it would likely be from a black hole of this size. That's why researchers are so focused on studying the fine details of this object. It could one day be the first to yield observational clues about this elusive quantum phenomenon. Let's also consider the fascinating astrophysical implications of its host binary system. XTE J1650-500 belongs to a class of systems known as low-mass X-ray binaries, LMXBs, where a compact object, typically a black hole or neutron star, accretes matter from a lower-mass companion star. The orbital dynamics of such systems are extremely informative, offering a way to estimate the mass of the black hole by observing the motion of the companion star. In XTE J1650-500's case, studies of Doppler shifts in the light emitted from the donor star have been used to constrain the black hole's mass. But beyond that, these binary interactions offer insight into the complex dance of gravitational, magnetic, and radiative forces that govern matter under extreme conditions. In this system, the donor star is believed to be less massive than our Sun and is gradually losing its outer layers as they are siphoned off into the black hole's accretion disk. Over time, this transfer of mass leads to dynamic changes in the system's behavior. Variability in X-ray output, changes in spectral state, and irregular outbursts all point to evolving conditions in the accretion environment. These behaviors are essential for understanding not just black holes but also broader phenomena like nova events, gamma-ray bursts, and kilonovae, all of which involve sudden, violent outflows of energy tied to compact object dynamics. And then there's the human dimension to this story. The very act of discovering XTE J1650-500 required not just technological prowess but a coordinated effort among international teams of scientists, utilizing spaceborne observatories like NASA's Rossi X-ray Timing Explorer, (XTE). That such a small and distant object can be located, analyzed, and even partially understood is a testament to humanity's capacity to peer into the void and make sense of the invisible. It exemplifies the intersection of theoretical physics, observational astronomy, data science, and engineering. Consider also the philosophical implications. XTE J1650-500 may be small by black hole standards, but it still contains several times the mass of our Sun crushed into a space smaller than a city. Its gravity is so intense that not even light can escape. Yet, paradoxically, this object is among the brightest X-ray sources in its region of the sky, thanks to the matter swirling around it. It is a paradoxical object, both hidden and revealed, destructive and generative, ancient yet active. And it exists as part of a narrative far greater than itself, contributing to the life cycle of stars, the distribution of elements, and the shaping of galaxies. From an educational standpoint, XTE J1650-500 is a rich case study. It allows instructors and students to explore core concepts in astrophysics such as blackbody radiation, spectral lines, relativistic effects, binary star evolution, and gravitational theory, all through the lens of one cosmic object. Textbooks and university lectures often reference high-profile black holes like those at the centers of galaxies. But stellar-mass black holes like XTE J1650-500 are more numerous and arguably more informative. They are closer, more dynamic, and more accessible for long-term study. In the next decade, as new telescopes like the Vera C. Rubin Observatory, the James Webb Space Telescope, and the Square Kilometre Array come fully online, we can expect to uncover even more black holes of this mass range, perhaps even smaller ones. Each new discovery will refine our understanding of the stellar death process and the mass distribution of compact remnants. And as our catalog of known black holes grows, XTE J1650-500 will remain an important reference point, the smallest known, the one that expanded our thinking, the one that whispered to us from the edge of what physics could explain. Even now, data from past observations of XTE J1650-500 is being reanalyzed with newer techniques, including machine learning algorithms trained to detect subtle patterns in time series data and spectral variability. These tools may reveal features that human observers missed, clues about quasi-periodic oscillations, spectral hardening, or minute shifts in line emissions that could yield new estimates of spin, inclination, or magnetic field strength. This demonstrates that our exploration of XTE J1650-500 is not over. In fact, we may only be scratching the surface. The deeper we peer into the enigma of XTE J1650-500, the more it serves as a mirror reflecting not just cosmic truths, but the frontiers of human understanding. Every layer we peel back on this unusually small black hole raises new and compelling questions. How stable are black holes of this size over time? Can they evaporate via Hawking radiation on observable timescales? And could there be even smaller black holes waiting to be discovered, ones that sit on the very edge of what's theoretically possible? To explore these questions, we need to understand the energetic environment that surrounds XTE J1650-500. Its accretion disk is a swirling cauldron of gas, dust, and magnetic fields. The infalling material doesn't plunge directly into the event horizon. Instead, it spirals inward, heating up due to friction and gravitational compression until it emits intense X-ray radiation. This radiation, though originating from just outside the event horizon, tells us everything we can hope to know about the hidden core. The X-ray spectrum shows shifts that correspond to the disk's temperature, motion, and even its structure. High-frequency quasi-periodic oscillations, which are flickering patterns in the X-ray light curve, have been detected from XTE J1650-500. These flickers likely originate from hot spots or turbulence in the innermost regions of the accretion disk, and some theories suggest that they may even be influenced by the black hole's spin. Spin is a crucial and elusive parameter in black hole physics. A spinning black hole drags spacetime along with it, a phenomenon known as frame dragging or the Lentz-Thirring effect. Determining the spin of XTE J1650-500 would not only reveal insights into its formation history but also offer a deeper test of general relativity in extreme conditions. Some initial studies have proposed that XTE J1650-500 might be spinning near the maximum possible rate, which is remarkable considering its size. If true, it suggests that the black hole was born with this spin or acquired it through prolonged, coherent accretion over time. Moreover, the environment around XTE J1650-500 is not static, it evolves. The accretion process is not a constant stream but more of a chaotic funnel, sometimes surging and other times subsiding. During outbursts, the accretion disk becomes brighter and hotter, releasing large amounts of X-rays. These outbursts may be triggered by instabilities in the disk or variations in the donor star's mass loss. Between these active phases, the black hole goes into a quiescent state, where its brightness drops by several orders of magnitude. These shifts provide a rare opportunity to study how black holes transition between different states, something that even supermassive black holes can't offer, due to their slower evolutionary timescales. XTE J1650-500 also plays a role in our ongoing attempt to catalog and classify black hole candidates in the Milky Way. While thousands of X-ray binaries are known, only a small fraction have been confirmed to host black holes. This requires precise measurements of their mass function, orbital parameters, and sometimes relativistic jets. In the case of XTE J1650-500, jet activity has been observed, suggesting the presence of a relativistic outflow of particles being accelerated away from the accretion disk. These jets are thought to be powered by magnetic fields tapping into the black hole's rotational energy via the Blandford's-Nagic mechanism. They are aligned perpendicular to the disk and can travel at speeds approaching the speed of light, carrying matter and energy far into the interstellar medium. This behavior brings XTE J1650-500 into the realm of microquasars, a category of stellar mass black holes that mimic the properties of quasars on a much smaller scale. In microquasars, jet activity, X-ray variability, and rapid state changes make them ideal laboratories for studying accretion physics. The scale of these systems allows astronomers to observe phenomena in days or weeks that would take millennia in supermassive black holes. As such, XTE J1650-500 serves as a kind of cosmic time machine, compressing eons of black hole evolution into observable human timescales. Another fascinating aspect is the possible connection between XTE J1650-500 and gravitational wave science. Although this black hole has not yet been associated with any detected merger events, systems like it are thought to be the progenitors of gravitational wave sources. When two such compact objects spiral together, they emit ripples in spacetime that can be detected by observatories like LIGO and Virgo. XTE J1650-500's relatively low mass suggests that if it had a similarly small companion, their merger might produce a gravitational wave signal in a frequency range where detectors are most sensitive. Though it currently exists as part of a binary with a non-compact donor, it's possible that future mass transfer or stellar evolution could tighten the orbit, transforming the system over millions of years. The long-term fate of XTE J1650-500 is also a matter of theoretical speculation. If the donor star continues to shed mass, it could eventually evaporate entirely, leaving a solitary black hole drifting through the galaxy. Alternatively, the system could undergo a nova-like explosion or even a second collapse event, depending on the mass dynamics. In any case, the black hole itself is unlikely to change much. It is the ultimate remnant, the final chapter in a star's life, and will persist for trillions of years, long after the last stars have burned out. Yet the most enduring mystery is the singularity at the heart of XTE J1650-500. According to general relativity, all the mass of the black hole is compressed into a single point of infinite density and zero volume. But such a concept breaks physics as we know it. Quantum mechanics refuses to permit a point of infinite density. Some physicists propose that the singularity is not a point at all, but a dense region of quantum foam, where the classical laws of spacetime give way to probabilistic chaos. Others suggest that the singularity might be a kind of holographic projection, storing information in a form we don't yet understand. These are not idle speculations. They are at the cutting edge of theoretical physics, and black holes like XTE J1650-500 provide the data necessary to either validate or falsify these ideas. We must also consider the technological marvels that have made this exploration possible. The instruments that detected XTE J1650-500, such as RXD, Chandra, and XMM Newton, are orbiting observatories equipped with advanced detectors capable of measuring X-rays from sources thousands of light-years away. These observatories rely on grazing incidence optics, cryogenic detectors, and precision time-stamping systems to build an accurate picture of events that unfold over milliseconds. On Earth, ground-based telescopes have complemented these efforts by studying the optical counterpart of the system, offering measurements of the companion star's radial velocity and spectral type. It's a multidisciplinary symphony of engineering, data analysis, and theoretical modeling, all orchestrated to understand something that can never be seen directly. And so, XTE J1650-500 is more than just a tiny black hole. It is a keystone in our effort to understand the universe, not only as it is, but as it could be. In it, we find the boundary between matter and mystery, between knowledge and speculation. We study it not because we can see it, but because its effects ripple across spacetime, leaving signatures in the light, gravity, and plasma that surround it. It is a shadow, yes, but it is a shadow that illuminates everything around it. Its very nature demands that we revise our understanding of stellar collapse, of the limits imposed by physical law, and of the strange balance between matter and gravity. When we look at XTE J1650-500, we are witnessing the remains of a star that once burned brightly, went supernova, and then, rather than dispersing its elements back into the cosmos, collapsed into a gravitational well from which not even light could escape. Yet from this darkness comes illumination, not literal light, but metaphorical enlightenment about the nature of mass, energy, and the geometry of space itself. The question often arises, how can something that doesn't emit light be studied in such detail? The answer lies in the powerful interplay of multi-wavelength astronomy and indirect measurement. We cannot see the black hole, but we can trace its fingerprints. These are encoded in the radiation emitted by the material falling into it, the motion of the companion star, the shape of the X-ray light curves, and even the polarization of X-rays, subtle signals that require sophisticated analysis. Instruments like NASA's NICER, Neutron Star Interior Composition Explorer, installed on the International Space Station, offer another avenue of exploration, capable of measuring brightness fluctuations with extreme precision. Though primarily focused on neutron stars, missions like this are part of a broader ecosystem of data that helps refine our models of accretion and compact objects. XTE J1650-500 exists in a delicate dance with its companion star, and this dance is what allows us to glean so much about the system. The orbital period of roughly 7.6 hours suggests a tight gravitational bond. The companion star, likely a main sequence or slightly evolved star, feeds the black hole through Roche lobe overflow. This means the star has expanded to the point that its outer layers are no longer gravitationally bound solely to itself, and the black hole's immense pull captures that material, funneling it into the accretion disk. This interaction alters both objects. The star loses mass, and the black hole grows, albeit very slowly. Tidal forces from the black hole also distort the star, heating it and affecting its magnetic field and surface activity. From a thermodynamic perspective, this is a process of entropy increase, disorder rising, energy transforming from one form to another, never lost, only shifted in structure. The accretion process releases more energy per gram than nuclear fusion, making black holes the most efficient engines in the known universe. Even the minuscule XTE J1650-500, with its tiny mass, can outshine entire galaxies in the X-ray spectrum during peak accretion phases. This staggering efficiency underscores the power of gravity, and how it can twist matter into forms of unimaginable energy density. And yet, there is a poetic symmetry to all of this. The black hole, a remnant of a star's death, draws life from its companion. It consumes and radiates, feeding not only on mass but on our curiosity. Its very existence challenges our preconceptions of scale and permanence. Is something that cannot be seen truly real? In physics, reality is defined not by visibility, but by interaction, by measurable influence. An XTE J1650-500 interacts with its environment in spectacular and measurable ways. Moreover, its discovery history is a narrative worth telling. Found in 2001 by the Rossi X-ray Timing Explorer, this object quickly gained attention because of the sharpness of its X-ray emissions and the unusual patterns in its light curves. Early analysis by astrophysicists such as John Miller and colleagues pointed toward a remarkably small mass, initially estimated to be around 3.8 solar masses, potentially even less. This immediately sparked debate, as it neared the theoretical boundary between neutron stars and black holes. Could it be a massive neutron star, masquerading as a black hole? Or was it truly a featherweight black hole, a celestial lightweight punching above its gravitational class? Further study pointed definitively toward the latter. The spectral analysis of its emissions showed features like a broadened iron K-alpha line, a hallmark of relativistic effects near a black hole's event horizon. This broadening occurs due to gravitational redshift and Doppler effects in the rapidly rotating accretion disk. These features could not be replicated by neutron stars, whose solid surfaces and magnetic fields would produce different observational signatures. It was increasingly clear that XTE J1650-500 was indeed a bona fide black hole, albeit one straddling the lower limit of mass and size ever observed. This opened a new frontier in black hole classification. If black holes could exist with masses this low, how low could they go? Were there even smaller ones, hiding in binary systems or roaming interstellar space as isolated remnants of ancient stars? Could primordial black holes, theorized to have formed in the early moments of the universe, exist with masses even below that of XTE J1650-500? And if so, how would we detect them? These are not idle questions. The search for the smallest black holes intersects with some of the biggest unsolved problems in astrophysics and cosmology. For instance, the idea of primordial black holes forming shortly after the Big Bang has been floated as a possible candidate for dark matter. If such objects exist, they would be extremely hard to detect, unless they occasionally collide with stars, pass through gas clouds, or, like XTE J1650-500, accrete from a binary companion. While XTE J1650-500 is not a primordial black hole, it's clearly the result of stellar collapse. It still serves as a proof of concept that nature allows black holes at or near the lower mass limit. In addition, studying these small black holes helps sharpen the criteria we use to distinguish them from neutron stars. Neutron stars are compact, ultra-dense spheres made almost entirely of neutrons, with a crust of exotic matter and a core that may contain strange quark phases. Their upper mass limit is not known precisely, but estimates suggest it lies around 2.2 to 2.5 solar masses, depending on the nuclear equation of state. Anything more massive than that cannot be supported by neutron degeneracy pressure and must collapse into a black hole. XTE J1650-500 sits just above this range, which makes it a key data point in refining these theoretical boundaries. And here lies a profound scientific opportunity: to use XTE J1650-500 as a natural laboratory for testing the limits of matter, gravity, and the fabric of spacetime itself. By probing the innermost regions of its accretion disk, analyzing the variability of its emissions, and modeling its spin and mass, we push our equations to the brink. If there are discrepancies between observation and theory, they could signal new physics, perhaps even a bridge between general relativity and quantum mechanics. Furthermore, the story of XTE J1650-500 also holds philosophical implications. It prompts us to reconsider our scale-centric view of the cosmos. We often think of black holes as enormous, monstrous phenomena consuming everything in their path. But XTE J1650-500 shows us that even the smallest black holes wield tremendous influence. It is the cosmic equivalent of a microblade, precise, efficient, and deadly in its gravitational pull. It may not be devouring stars wholesale, but it is reshaping its environment, altering the fate of its companion, and radiating signals that reach across thousands of light years to touch our instruments. What's more, it defies the traditional hierarchy of astronomical phenomena. It is not a supernova, nor a neutron star, nor a pulsar, but it carries the echoes of all three. It was likely born from a supernova, would have passed through a neutron star-like phase in its collapse, and emits radiation in bursts that can mimic the pulsed emissions of a pulsar. In this way, it is a fusion of identities, a hybrid monument to the death throes of a massive star and the chaotic beauty of extreme physics. There is also the poetic irony that something so small in the vast cosmos can teach us so much. A black hole barely larger than a city has become a nexus for astrophysics, a magnet for data, and a springboard for theory. It's a lesson in humility and perspective, reminding us that scale is not always correlated with importance. Sometimes, the smallest things cast the longest shadows, especially when they bend space-time itself. It also raises the question of detection bias in astrophysics. Are we only seeing black holes like XTE J1650-500 because they happen to be in binary systems? How many more small black holes are lurking in the galaxy, undetected because they lack a luminous companion or significant accretion activity? These objects could number in the millions, each one a quiet monument to stellar death. Without the telltale signs of X-ray flares or gravitational interactions, they would remain hidden, dark ghosts in a luminous universe. This realization has pushed scientists to explore new detection methods. One promising avenue is gravitational microlensing, where a black hole passes in front of a distant star and magnifies its light through gravitational lensing. This technique doesn't require the black hole to emit radiation. It only needs to exist and bend light, a feat all black holes are adept at. Microlensing surveys, such as those conducted by the OGLE and MOA collaborations, have identified candidates that may be isolated black holes, including ones possibly in the mass range of XTE J1650-500. Though challenging to confirm, these detections could point to a hidden population of stellar remnants. Another possibility is detecting gravitational waves from black hole mergers. Since the groundbreaking LIGO/Virgo discoveries, we've begun to catch the tremors of space-time caused by colliding black holes. While most detected mergers so far involve larger black holes, tens of solar masses, future improvements in detector sensitivity could open the door to spotting mergers involving smaller ones. If XTE J1650-500 had a twin, and the two spiraled into each other over millions of years, they could release a final burst of gravitational energy that tells us not just of their death, but of their existence. In this way, the smallest black holes may be the key to unlocking the biggest mysteries. They challenge the boundaries of known physics, test our observational methods, and stretch the limits of what can be inferred from faint, fleeting data. They also hint at a deeper symmetry in nature. Just as the tiniest particles, quarks, electrons, form the foundation of atoms and molecules, so too do the smallest black holes remind us that fundamental truths are not always tied to enormous scales. Sometimes it is in the quiet, in the shadows, and in the minuscule, that we find the clearest echoes of the universe's most profound laws. In observing and studying XTE J1650-500, we aren't just looking at a black hole. We are looking at a boundary, the border between what collapses and what persists, between what is seen and what must be inferred. It is a portal, not in the science fiction sense, but in the scientific one, a threshold beyond which current understanding thins and bends, just as light bends near its event horizon. And as we push deeper into that threshold, we are not just learning about a singular celestial body, we are confronting the architecture of reality itself. But XTE J1650-500 is not the only low-mass black hole that has caught the attention of astrophysicists. There is a broader context here, a class of so-called mass gap objects, stellar remnants that fall between the highest mass neutron stars and the lowest mass black holes. Theoretical models long predicted a gap in mass between about 2.5 and 5 solar masses, a no-man's land where neither neutron stars nor black holes should comfortably exist. And yet, XTE J1650-500 defies this gap, existing right where conventional theory wavers. It invites us to rethink stellar collapse models, to revisit the nuclear equations of state, and to ask whether exotic processes, such as delayed supernova fallback or asymmetric explosions, might account for such small black holes. These are not just academic curiosities. Understanding the formation and frequency of low-mass black holes could help explain galactic evolution, binary star life cycles, and even the rate at which black hole mergers occur across the universe. It affects the way we simulate cosmic structure formation, the distribution of compact objects in galaxies, and the future of black hole population synthesis models. It shapes the story of how the universe recycles matter, through birth, death, and collapse. Perhaps most strikingly, XTE J1650-500 brings a sense of intimacy to an otherwise grand and distant cosmos. It is not a monster lurking in the galactic core, nor a supermassive leviathan warping space around quasars. It is a remnant, a quiet echo of stellar violence, situated in the Milky Way, a neighbor in cosmic terms. And yet, through its subtle pull and flickering emissions, it exerts a gravity not just on its companion star, but on our minds. It draws us in, compelling us to look closer, think deeper, and reach further. What began as a faint X-ray signal now resonates across scientific journals, theoretical models, and the very language of astrophysics. It reminds us that sometimes the smallest signals carry the loudest messages, not in volume, but in implication. XTE J1650-500 is more than a number in a catalog. It is a cosmic whisper, challenging us to listen closely. And as we lean in to listen, we find ourselves immersed in a narrative that spans epochs. XTE J1650-500 did not just emerge spontaneously. It is the final act of a star's long and complex life. Millions, perhaps billions, of years ago, a massive star was born from a cold, dense region of interstellar gas, somewhere in our galaxy. It shone for ages, fusing hydrogen into helium, then heavier elements, each step a march toward an inevitable collapse. And when that final fusion process could no longer counteract the pull of gravity, the star met its fate, not with a whimper, but likely with a brilliant explosion, a supernova that for a brief moment may have outshone the entire galaxy. But unlike many of its peers that left behind neutron stars or large black holes, this progenitor star's core did something unusual. The collapse didn't yield a massive object, but a compact, tightly bound core with just a few solar masses, perhaps only 3.8 times the mass of our Sun. This result challenged every assumption held by astrophysicists at the time. For decades, textbooks were built on the belief that any remnant of stellar collapse above around 2.5 solar masses must form a black hole, while anything below remained a neutron star. Yet here was a black hole potentially tipping the scales at less than 4 solar masses. XTE J1650-500, in this light, wasn't just an object, it was a riddle. The exact process that leads to the formation of such a low-mass black hole is still debated. One hypothesis suggests that the supernova explosion may not have expelled all the stellar material. Some of it might have fallen back onto the protoneutron star, pushing it over the edge into a black hole. But if so, why did the final mass remain so low? Was the explosion unusually efficient at expelling material? Did rotation or magnetic fields play a role? Or does this object hint at an entirely new mode of stellar death, one that bridges the gap between neutron stars and black holes? This mystery becomes more complex when considering XTE J1650-500's binary nature. Its companion star, from which the black hole draws material, is of particular interest. The gravitational pull of XTE J1650-500 siphons matter from this companion, forming an accretion disk that heats up and glows in X-rays, making the system visible to Earth-based and orbital telescopes. It is through this disk that the mass of the black hole was inferred. Observing the way the companion star wobbles, its radial velocity, allowed astronomers to calculate the mass of the unseen companion. The results consistently pointed to an object too massive to be a neutron star, and yet possibly the lightest black hole ever detected. This process, using companion dynamics to weigh invisible objects, is an extraordinary feat of indirect science. Imagine trying to measure the weight of an unseen dancer by watching the motion of a partner in a dark room, illuminated only by flashes of strobe light. And yet, astronomers have become adept at this detective work, refining their models, calibrating their tools, and converging on a consensus. XTE J1650-500 is a black hole, and a light one at that. But even this raises deeper philosophical questions. What does it mean to call something a black hole? Is it simply any object with a gravitational field strong enough that nothing, not even light, can escape? Or is it more than that, a phase of matter, a singularity cloaked by an event horizon, a tear in the fabric of space and time? In the case of XTE J1650-500, we are forced to apply these profound definitions to an object not much larger than a city. The event horizon of such a small black hole would span only about 11 kilometers in radius, barely enough to cover a suburban town. And yet this minuscule region would represent the end of physics as we know it: infinite density, curved space, and trapped light. The implications of this are staggering. The very existence of such a tiny black hole challenges our understanding of general relativity and quantum gravity. At these scales, quantum effects may no longer be negligible. Could it be that XTE J1650-500, in some way, holds clues to the long-sought theory of quantum gravity? Could its formation and structure hint at the mechanics of Hawking radiation, or the elusive firewall paradox? We don't yet know, but every piece of data we collect from this system could bring us one step closer to those answers. Meanwhile, XTE J1650-500's accretion activity provides a living laboratory. As matter spirals into the black hole, it heats up and emits radiation across the electromagnetic spectrum. By studying these emissions, especially in X-rays, scientists can analyze the behavior of matter under extreme gravity. The inner regions of the accretion disk orbit at relativistic speeds, close to the speed of light, and their radiation becomes redshifted, warped, and smeared. This spectral broadening has been observed in XTE J1650-500 and used to infer properties such as its spin. Spin is another tantalizing mystery. Black holes, like particles, have three defining properties: mass, charge, and spin. Most astrophysical black holes are neutral, so spin and mass become the key observables. In 2002, some astronomers suggested that XTE J1650-500 might be spinning extremely fast, near the theoretical maximum. If true, this would imply that the collapsing star had an enormous amount of angular momentum, and that very little of it was lost in the explosion. But how does such a small black hole maintain such a high spin? What mechanisms drive or dampen this rotation? And could this spin affect the black hole's interaction with its environment, its jet formation, or even the gravitational waves it might someday emit? The idea of a spinning, low-mass black hole is both exotic and exhilarating. Spin affects the shape of the event horizon, the innermost stable orbit of the accretion disk, and the potential for matter to escape as relativistic jets. If XTE J1650-500 indeed possesses such spin, it may be helping to launch invisible jets of plasma into space, jets that, if detected, could further refine our models of black hole physics. And yet, despite decades of observation, there is still so much we do not know. Instruments come and go. X-ray satellites like XTE, Chandra, and XMM Newton have peered into this system, each revealing new pieces of the puzzle. But no observation is complete. Every spectrum taken is just a snapshot, a brief look into a dance that has been unfolding for millions of years. The light we receive is filtered through cosmic dust, distorted by gravitational lensing, and diluted by distance. We must reconstruct the nature of XTE J1650-500 from whispers, light years away and filtered through complex theoretical models. Still, the story continues. As new instruments come online, like the James Webb Space Telescope or future X-ray observatories, our view will sharpen. We may detect more low-mass black holes, refine the mass of XTE J1650-500, or discover that it is not alone. Perhaps it is part of a hidden population, a class of faint, low-mass black holes born from a unique stellar lineage. Perhaps there are millions more like it, spread across the galaxy, waiting to be revealed not in brilliance, but in subtlety. Or perhaps XTE J1650-500 is unique, a cosmic anomaly, the result of a specific and rare confluence of conditions that may never be repeated. If this is true, then understanding it becomes all the more urgent. Singular objects in astrophysics often serve as gateways to new understanding. Just as pulsars were once considered anomalies before revealing the existence of neutron stars, XTE J1650-500 might be a window into a previously hidden mechanism of stellar evolution or gravitational collapse. Its uniqueness also draws us to a larger question: how common are black holes of this size? Historically, black holes discovered in binary systems have masses ranging from about 5 to 20 solar masses. Neutron stars, on the other hand, typically fall between 1.2 and 2.5 solar masses. The gap between 2.5 and 5 solar masses has long been considered a mass gap, a strange absence of objects. But XTE J1650-500 might sit squarely within that gap. Could this object be the first of many to shatter our assumptions? Could it suggest that the so-called mass gap isn't real but rather an artifact of our observational limits? Or worse, could it imply that our models of stellar death and core collapse are fundamentally incomplete? To answer this, we must look to other potential candidates. Over the last few decades, gravitational wave observatories like LIGO and Virgo have started detecting black hole mergers. These mergers allow astrophysicists to indirectly observe the masses of black holes through the gravitational waves they emit as they spiral into one another. Fascinatingly, some of these mergers have also hinted at black holes within or near the lower end of the mass spectrum. However, it's difficult to reconcile these results with those from X-ray binary systems like XTE J1650-500. The environments are different, the data is different, and the models used to interpret them are built on different assumptions. And yet, the convergence is tantalizing. As data accumulates from all sides, X-ray binaries, gravitational waves, gamma-ray bursts, and more, a fuller picture may emerge. It's possible that there exists a continuum of compact objects, some of which blur the line between neutron star and black hole. In this context, XTE J1650-500 may be the Rosetta Stone, a key to interpreting an entire class of objects we've only just begun to identify. Furthermore, its behavior provides even more insight. The variability of its X-ray emissions, the flickering and pulsing of high-energy light, tells us about the structure of its accretion disk and the inner edge of stable orbits around the black hole. These variations are not random. They're governed by deep physical principles. By performing Fourier analysis on the X-ray light curves, astronomers can detect quasi-periodic oscillations, QPOs. These QPOs are believed to be related to the matter orbiting just outside the event horizon. For XTE J1650-500, high-frequency QPOs have been detected, suggesting that the inner disk is incredibly close to the black hole itself, yet another hint that it is spinning rapidly. The presence of QPOs allows for yet another method of estimating the black hole's mass. By comparing the observed frequencies to theoretical models, astronomers can estimate the radius of the innermost stable circular orbit, which in turn can be related to the mass and spin of the black hole. Interestingly, the values derived from this method for XTE J1650-500 tend to support the claim that it is one of the smallest known black holes, with a mass potentially as low as 3.8 solar masses. However, some controversy surrounds this number. Other researchers have proposed slightly higher mass estimates, ranging up to 7 solar masses, depending on the assumptions made in their models. This variability highlights the difficulty in measuring such distant and extreme objects. Every parameter, from the inclination of the system to the mass of the companion star to the distance from Earth, affects the final mass calculation. Small errors can lead to big differences. Still, even the upper bound estimates keep XTE J1650-500 near the low end of the known black hole mass spectrum. Beyond its mass, the system's evolution is another area of rich study. Binary systems like this one evolve over time as gravitational radiation, mass transfer, and magnetic braking alter their orbital parameters. Eventually, some may merge, others may separate, and some may remain in a stable dance for billions of years. For XTE J1650-500, the companion star appears to be a low-mass object, perhaps less than half the mass of the Sun. This star likely began transferring mass to the black hole early in its life, and as it does, it loses angular momentum and mass, spiraling slowly inward. This process has consequences. Over time, the system becomes tighter and the accretion rate may change. Periods of intense activity, outbursts, can occur when the accretion disk suddenly becomes unstable and dumps a large amount of matter onto the black hole. This is likely what happened in 2001 when XTE J1650-500 was first discovered. It flared up in X-rays, becoming temporarily one of the brightest sources in the sky, before fading back into obscurity. Such outbursts are not uncommon in these systems, but they are crucial moments for study. They reveal otherwise hidden features, allowing for detailed spectroscopy, timing analysis, and more. When an outburst occurs, astronomers scramble to observe it across all wavelengths: radio, optical, ultraviolet, X-ray, and sometimes even gamma rays. This multi-wavelength approach is necessary because black hole systems emit radiation from multiple regions. The inner disk emits X-rays. The outer disk and companion star contribute optical and UV, and relativistic jets, if present, can emit radio waves. In the case of XTE J1650-500, coordinated observations during its 2001 outburst provided one of the most detailed views ever obtained of a black hole accretion event. These observations confirmed the presence of relativistically broad and iron lines in its spectrum, a smoking gun for the inner accretion disk orbiting near the event horizon. The broadening is caused by both Doppler shifts from the high orbital velocities and gravitational redshift due to the intense curvature of spacetime. Such iron lines are among the most powerful diagnostic tools in black hole astrophysics. They allow scientists to measure not only the inner disk radius but also to infer the spin of the black hole itself. For XTE J1650-500, this iron line indicated that the black hole may be spinning close to its theoretical maximum, what physicists call a curved black hole. This opens the door to yet another series of questions. If the black hole is spinning so rapidly, how did it acquire that spin? Was it born spinning, or did it gain angular momentum through accretion? And what does this spin mean for the possibility of jet formation? Jets, collimated beams of plasma traveling near the speed of light, are often observed in black hole systems, particularly in those with high spin. While no major jets have been conclusively observed in XTE J1650-500, the presence of high spin and certain radio emissions suggests that jet activity may exist but has simply gone undetected or was transient. If jets are confirmed, they would provide another avenue to study the magnetic fields and particle acceleration processes near the event horizon. Even without confirmed jets, XTE J1650-500 remains a goldmine for relativistic astrophysics. It sits at a crossroads, between mass regimes, between theoretical models, between observational methods. Its small size makes it an outlier, but that very status makes it invaluable. Like the first discovered neutron star, or the first detected exoplanet, XTE J1650-500 has the power to redefine categories and expand boundaries. And yet, the story is not over. As telescopes become more sensitive, as models become more refined, and as new observational methods, like polarimetry or next-gen gravitational wave detection, become available, our understanding will deepen. Perhaps XTE J1650-500 will become a reference point, a touchstone against which all small black holes are measured. Or perhaps it will remain an outlier, a reminder of how little we truly know, even after centuries of looking skyward. If it remains an outlier, the questions it raises may be more valuable than the answers it provides. That is the nature of anomalies in science. They challenge consensus, reveal weaknesses in our theories, and inspire new lines of inquiry. In the case of XTE J1650-500, the questions are many. Are black holes this small truly rare, or have we just not looked in the right way? Could our instruments be biased toward detecting more massive black holes, leaving a population of low-mass ones invisible in the cosmic background? What role does the binary companion play in the apparent characteristics of the system, and are we perhaps misattributing some features to the black hole that arise from interactions between the two bodies? The uncertainty even opens the door to exotic alternatives. For instance, if XTE J1650-500 isn't a conventional black hole, could it be something stranger? Could it be a primordial black hole? Hypothetical black holes formed not from stellar collapse but from density fluctuations in the early universe? These objects are often invoked in discussions about dark matter and early cosmic evolution. Though no confirmed primordial black hole has been observed, XTE J1650-500's unusual characteristics tempt speculation. Or could it be something even more radical, an object not fully collapsing into a singularity? Theoretical constructs such as gravastars or boson stars have been proposed as alternatives to black holes. These hypothetical objects mimic some of a black hole's observational features but avoid the paradoxes associated with event horizons and singularities. While there's currently no direct evidence supporting such exotic possibilities in the case of XTE J1650-500, its peculiarities at least warrant keeping an open mind. More realistically, though, it's likely that XTE J1650-500 is a normal black hole in a particularly informative corner of parameter space, one that tests the limits of our observational methods and our physical understanding. It challenges our mass estimations, it probes our models of core collapse, and it stresses our understanding of accretion physics and relativistic spin. All of this, in turn, pushes the boundaries of high-energy astrophysics. As such, future study will benefit from new observational tools. Missions like the James Webb Space Telescope, while optimized for infrared, could help identify companion stars or study the effects of the system on surrounding dust. More critically, upcoming X-ray observatories such as Athena, Advanced Telescope for High-Energy Astrophysics, or the Chinese XTE mission, Enhanced X-ray Timing and Polarimetry mission, will bring higher resolution and sensitivity to systems like XTE J1650-500. These instruments will allow researchers to probe more deeply into the X-ray spectra, variability, and polarization, unlocking new layers of information about magnetic fields, disk structure, and even space-time geometry near the event horizon. Meanwhile, ground-based observatories will continue refining measurements of distance and optical variability, which remain crucial for pinning down fundamental properties like mass and spin. Radio telescopes may eventually detect subtle jet emissions or signs of synchrotron radiation, while gravitational wave detectors might, someday, catch a merger involving such a small black hole, adding an entirely new line of data to the mix. What makes XTE J1650-500 so captivating is that it exists at the edge of what we understand. Its existence alone confronts our theories with a living, luminous contradiction. It is not just a black hole, it is a puzzle, a frontier, a challenge. And in that sense, it represents the essence of astronomy itself. Every observation, every outlier, every flickering point of light in the night sky is a message. Some confirm what we know, others, like XTE J1650-500, whisper of everything we do not. And we listen not only with our instruments and equations, but with our imaginations. For in the cosmos, The smallest anomalies often carry the heaviest weight. XTE J1650-500, in its deceptively diminutive mass, may very well anchor a gravitational pull on the direction of astrophysical research for decades to come. What it lacks in size, it more than makes up for in potential. Because at the very heart of this faint X-ray source lies something extraordinary, perhaps the most compact stellar remnant nature has yet shown us, a cosmic punctuation mark where a star once shone. To appreciate the full significance of this object, we must revisit what defines a black hole in the first place. A black hole is not merely a collapsed star, it is a place where the very geometry of space and time is twisted beyond recognition. The boundary surrounding it, the event horizon, marks a point of no return. For massive stars that exhaust their nuclear fuel, the collapse is inevitable. The only uncertainty is what mass and spin their core retains and whether it becomes a neutron star or a black hole. That threshold, the tipping point where gravity overwhelms all other forces, is where XTE J1650-500 hovers, like a balancing act frozen in time. If it truly has a mass of 3.8 solar masses or even less, it would press hard against that theoretical boundary. Is it possible, then, that nature occasionally produces black holes right at the edge, in that narrow, uncertain window where collapse might just barely win against the resistance of neutron degeneracy pressure? This object offers a chance to explore that ambiguous twilight zone, and every new piece of data about it brings us closer to drawing the line with confidence. The process of measuring a black hole's mass is itself fraught with complexity. Astronomers typically rely on observations of a companion star's motion, measuring its orbit via Doppler shifts and spectral lines. But these measurements depend heavily on assumptions: the inclination of the orbit, the mass of the companion, and the system's distance from Earth. A small error in inclination, for example, can lead to significant underestimation or overestimation of the black hole's true mass. This is one reason why estimates for XTE J1650-500 have shifted since it was first studied. One team might place the mass under 4 solar masses, while another might revise that figure upward to closer to 6. Still, even on the high end of these estimates, XTE J1650-500 remains in an elite category: black holes near the minimum known mass. Most confirmed stellar mass black holes are significantly heavier, ranging from 5 to 10 solar masses, with many even heavier than that. The rarity of low-mass black holes could suggest a true lower limit, perhaps reflecting a natural cutoff in the stellar collapse process. Or it might just reflect observational bias, meaning we simply haven't been able to find these smaller ones as easily due to their lower luminosity or more elusive accretion behaviors. Adding another layer to this mystery is the matter of the black hole's spin. Observations from NASA's Rossy X-ray Timing Explorer, RXT, which initially discovered the object in 2001, indicated XTE J1650-500 could be spinning at nearly the maximum rate allowed by general relativity. That means it might be rotating close to the speed of light. If true, this has profound implications. The spin of a black hole tells a story about its birth and evolution. Was it born spinning so fast, flung into the cosmos with a violent rotational legacy from its progenitor star? Or did it gain that spin through a process of accretion, gradually pulling in matter from its companion star over millions of years? High spin affects not only the black hole's immediate environment, but also the very shape of spacetime around it. It drags space itself in a phenomenon known as frame dragging, predicted by Einstein and confirmed in a variety of observational settings. It also alters the behavior of the accretion disk, the swirling platter of hot gas spiraling into the event horizon. In rapidly spinning black holes, the innermost stable circular orbit, ISCO, draws closer to the event horizon. This means matter can orbit closer, and the gravitational energy extracted from infalling gas becomes greater, leading to more intense X-ray emissions. XTE J1650-500's X-ray signature, particularly during its 2001 outburst, gave scientists an opportunity to analyze these dynamics in unprecedented detail. The X-ray spectrum displayed features consistent with relativistically broadened iron emission lines. These lines, smeared and shifted due to the immense gravity of the black hole, serve as fingerprints of conditions in the innermost regions of the accretion disk. By modeling these lines, astrophysicists can estimate the radius of the inner disk, and from that, infer the black hole's spin. It's through this intricate analysis that researchers like Dr. John Miller of the University of Michigan and others proposed XTE J1650-500 could be spinning at near the theoretical limit. But here again lies uncertainty. Iron line modeling involves complex simulations, assumptions about disk geometry, and the effects of scattering, ionization, and more. Different models can lead to different conclusions. Yet if the high-spin interpretation is correct, then XTE J1650-500 becomes a dual anomaly, possibly the smallest known black hole, and one of the fastest spinning. That's a rare combination and a rich subject for theoretical exploration. If we entertain the possibility that it really is this compact and this fast spinning, then we must also grapple with its formation history. Did its progenitor star collapse in a supernova, or undergo a direct collapse with minimal explosion? How does such a small remnant form from a star likely several times more massive than the Sun? Some models suggest that direct collapse leads to more massive black holes, while others show that under certain conditions, fallback of matter after an explosion can result in smaller remnants. It's plausible that the progenitor of XTE J1650-500 experienced significant mass loss before collapsing. This could have been due to powerful stellar winds, especially if the star had high metallicity. Alternatively, the presence of the binary companion could have siphoned off mass over time, altering the evolution of the primary star. In this light, XTE J1650-500 becomes more than a black hole. It becomes the fossil record of a long, complex stellar life, shaped by both internal and external forces. The companion star, though less famous than its collapsed partner, also plays a crucial role. It is the source of the black hole's accreted matter, the fuel that generates the X-ray emissions we observe. By studying the variability, temperature, and orbital motion of this companion, researchers hope to pin down more precise estimates of the black hole's properties. However, the star is faint and distant, making such studies difficult. In future, more powerful optical telescopes may finally allow us to take a better look at this essential but elusive partner. Even more intriguingly, the interaction between the black hole and its companion may produce periodic outbursts. These events, during which the system brightens dramatically in X-rays, provide windows of opportunity to gather data. During the 2001 outburst, for example, the system exhibited quasi-periodic oscillations, QPOs, rapid fluctuations in X-ray intensity that may be tied to orbiting matter close to the event horizon. Studying these QPOs can yield insights into the inner workings of the accretion disk and the structure of spacetime itself. QPOs in XTE J1650-500 were observed at frequencies up to hundreds of hertz, consistent with expectations for a black hole of a few solar masses. These oscillations can be thought of as the echoes of matter dancing at the edge of oblivion, offering tantalizing glimpses into the relativistic world just outside the event horizon. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.